No one who boards a generation ship will ever arrive, and no one who arrives ever chose to leave. 8 generations of human beings, living and dying in the void between 2 stars. This is what a generation ship would actually experience on its way to Proxima Centauri. What does 500 years of absolute void actually do to the human beings trapped inside it? If your brain is already working overtime on this, make sure to give this video a like. Now let's get started. Proxima Centauri sits at roughly 40 trillion kilometers from where you are sitting right now. For a long time, that number existed only as an abstraction, a figure astronomers calculated and then quietly set aside because there was nothing meaningful to do with it. Then, in 2016, everything shifted. Scientists announced a discovery that changed the conversation entirely. There is a planet orbiting Proxima Centauri, a rocky world sitting inside the star's habitable zone, the region where liquid water could theoretically exist on a surface. Named Proxima Centauri b, it carries a mass approximately 1.27 times that of Earth, completes a full orbit in just 11 Earth days, and sits at 4.24 light-years away. The closest star to our own Sun has a planet that could, in theory, and with enormous caveats we will absolutely get into, host conditions relevant to life. That discovery, published in the journal Nature, transformed Proxima Centauri from an interesting footnote into an address, a destination. For the first time in human history, we had a specific place to point to and say, that is where we might go. The question was never whether we wanted to go. The question is whether any version of us that we would still recognize as human could survive the attempt. A generation ship, as the concept appears in serious scientific literature and engineering proposals, is not a vessel carrying a crew of astronauts on a mission. It is a moving civilization, a self-contained world, sealed and launched, designed to keep a human population alive, healthy, and this word does a lot of work, sane, across potentially hundreds of years of travel. We are not talking about hibernation pods or suspended animation. Those technologies do not yet exist at any scale that would apply here. We are talking about real people, living real lives, having children, raising them, watching them grow old and dying, all without ever setting foot on solid ground. The most discussed travel velocities for a crewed vessel range between 1 and 5% of the speed of light. At 5%, roughly 15,000 kilometers per second, the journey takes approximately 85 years. That is long and it is brutal, but it is technically within the span of a single extended human lifetime. Someone who boards at 20 might, just barely, live to see arrival. At 1% of the speed of light, however, you are looking at 420 years. That is longer than the United States has existed as a nation, longer than the gap separating us from Shakespeare, longer than any institution, government, religion, or cultural identity has remained coherent and unified in recorded history, which raises a question that engineers tend to skip over. How do you keep a society together across 4 centuries with nowhere to go and no way out? We will return to that because the answer is not simple and some of the implications are genuinely troubling. But first, the physics. Because before the sociology gets complicated, the environment tries to kill you. For the first portion of the voyage, the early decades, the ship is still, in a very real sense, inside the extended influence of our solar system. This surprises most people. We tend to imagine space as beginning at the edge of Earth's atmosphere, or perhaps at the Moon's orbit. But the Sun's reach extends far further than that. The heliosphere, the vast magnetic bubble generated by the Sun's solar wind, stretches outward for roughly 100 astronomical units in most directions. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. So the heliosphere spans roughly 15 billion kilometers. That is the bubble of charged particles and magnetic fields our Sun continuously pumps into surrounding space, and it acts as a shield, deflecting a significant portion of galactic cosmic radiation before it can reach the inner planets, beyond the outer edge of that bubble. The boundary scientists call the heliopause. The solar wind stops abruptly. The ambient material of the galaxy takes over, particle energies spike, the radiation environment becomes dramatically more hostile. Any ship crossing that threshold needs shielding capable of protecting its crew from galactic cosmic rays. High-energy particles accelerated by distant supernova explosions, moving at fractions of the speed of light themselves, punching through ordinary matter with ease. But even the heliopause is not the true edge of our solar system. The Oort cloud, a vast, spherical shell of icy bodies, cometary nuclei, and frozen debris thought to surround the Sun at enormous distances, begins at roughly 2,000 astronomical units and extends outward to perhaps 100,000 astronomical units. That is approaching 2 light-years. Nearly halfway to Proxima Centauri, the generation ship would spend years crossing this region. The Oort cloud is so diffuse that a direct collision with any of its objects is vanishingly unlikely. The distances between individual bodies out there are vast beyond comprehension, but it represents a profound conceptual threshold. Clearing it means leaving the last gravitational embrace of the Sun. It means stepping into the true interstellar gulf, and that gulf is not empty. This is one of the most persistent and consequential misconceptions about deep space, that the void between stars is a perfect vacuum. It is not. The interstellar medium, the material filling the space between stellar systems, consists of gas, dust, magnetic field lines, and a constant background of cosmic radiation. The average density is extraordinarily low, around 1 atom per cubic centimeter, sometimes less. But at the speeds a generation ship would travel, even that near emptiness becomes a serious engineering concern. At 1% of the speed of light, hydrogen atoms in the interstellar medium impact the ship's forward hull with energies equivalent to low-level ionizing radiation. At 5%, the flux intensifies. The bow of the ship is perpetually bathed in a stream of particles that over decades would degrade unprotected materials and accumulate biological damage in any crew member unfortunate enough to be stationed near it without adequate shielding. Several proposals attempt to address this. One involves a magnetic field projected ahead of the ship, a kind of artificial magnetosphere that would deflect ionized particles around the hull. Another uses a physical shield at the bow, a thick layer of material, perhaps polyethylene or water ice, designed to absorb impacts and slowly ablate away over the centuries of flight. A third, more speculative concept imagines using the hydrogen itself as fuel, scooping it from the interstellar medium with a vast electromagnetic funnel, a concept called the Bussard ramjet, proposed in 1960, and burning it in a fusion reaction to power continued acceleration. Each of these ideas carries its own cascade of engineering challenges. None of them have been built. None of them have been tested at scale. And yet, every generation ship concept depends on solving at least one of them. Here is something almost nobody discusses when imagining this voyage: what the sky would actually look like from inside the ship. We picture it as familiar, a star field roughly resembling what you see on a clear night, maybe a little darker, a little more vivid. But the reality is more alien than that. First, stars in space do not twinkle. The scintillation we see from Earth is entirely a product of our atmosphere, which refracts and distorts incoming light as it bends through layers of different temperature and density. Remove the atmosphere, and every star becomes a perfectly steady, unwavering point of light. The sky would feel different in a way that is hard to articulate, more precise, somehow, colder, more honest. Second, as the ship accelerates toward Proxima Centauri, something called relativistic aberration begins to subtly distort the apparent positions of stars across the sky. Stars ahead of the ship shift slightly toward the direction of travel. They seem to crowd together in the forward hemisphere. Stars behind shift toward the rear. Simultaneously, the Doppler effect tints forward stars slightly toward blue and backward stars toward red. At 5% of the speed of light, these effects are subtle but real. An astronomer born on the ship, mapping the sky with instruments, would find a universe that doesn't quite match the star charts compiled on Earth. By the time the ship approaches Proxima Centauri, after generations of travel, that destination star will have grown from a faint, reddish smudge into the dominant light in the sky, brighter than anything else. Then, as the ship decelerates into the system, it will resolve into something no human eye has ever witnessed up close. A red dwarf star, smaller and cooler than our Sun, surrounded by at least 2 known planets, one of which might be waiting. But before we get to arrival, before we talk about what Proxima Centauri b might actually look like up close, and what the crew would find when they got there, there is something that happens in the middle of this journey, something that the engineering documents, the mission architecture papers, the propulsion studies, almost none of them adequately address. The people on that ship will stop thinking of themselves as travelers. They will start thinking of themselves as home. Before we go inside that ship, there is a particular kind of silence that happens when you point a telescope at Saturn for the first time and the rings resolve. The telescope I use for casual backyard observation and genuinely recommend to anyone starting out is the Celestron StarSense Explorer. What makes it unusual is that it uses your smartphone to map the sky in real time and guide you to whatever you want to find. Nebulae, planets, star clusters, objects that took astronomers centuries to catalogue, accessible to you on a clear evening with no prior experience required. You do not need to know the sky to begin knowing the sky. If you want to see the kind of objects we talk about on this channel with your own eyes, make sure to check out this telescope. It's in the description and pinned on the comments. Now back to the ship, and back to what isolation at this scale actually does to a mind. Let us set the scene carefully, because the details matter here. Imagine the vessel is approximately 80 years into its journey. The original crew, the men and women who trained for this, who volunteered, who kissed their families goodbye on a launch pad somewhere and watched Earth shrink into a blue marble and then into nothing. Most of them are gone now. The eldest among the original passengers are in their final years. The generation now running the ship's systems, maintaining its engines, monitoring its course, was born in transit. Every single person of working age has known nothing but this hull, this recycled air, this artificial lighting calibrated to simulate a 24-hour day cycle that no longer corresponds to any planetary rotation anywhere near them. For these people, Earth is not a memory, it is a story, a collection of recordings, documents, photographs, and the increasingly emotional testimonies of aging grandparents. It holds roughly the same experiential weight that ancient Rome holds for someone alive today, intellectually real, historically significant, and completely beyond the reach of the senses. The destination, meanwhile, Proxima Centauri, is still a point of light, still unreachable within any individual lifetime, still abstract, still a promise made by people who are now buried in the ship's interior. In whatever arrangement the mission architects designated for human remains in a closed ecological system, this is the psychological terrain that researchers have begun to map with increasing seriousness, particularly as organizations like NASA and the European Space Agency have funded studies on long-duration isolation. And what those studies reveal is not simply that isolation is unpleasant. It is that isolation at this scale, multi-generational, inescapable, purposeful, creates a specific and deeply strange form of human consciousness. One of the most significant findings in isolation psychology comes not from space research, but from terrestrial analogues, Antarctic winter-over stations, nuclear submarines, and long-duration habitat simulations like the High Seas missions conducted in Hawaii, where small crews spent up to a year in confined quarters simulating a Mars mission. What these environments consistently produce, beyond the expected stress and friction, is something researchers call third quarter syndrome. The pattern is remarkably consistent. In a long, isolated mission, the first quarter tends to be characterized by heightened alertness, motivation, and group cohesion. Everyone is new to this. The novelty carries people. The second quarter settles into routine, comfortable for some, deadening for others. Then the third quarter hits. Roughly 3/4 of the way through a mission, before the end is truly in sight, but after the beginning feels ancient, a specific kind of psychological deterioration tends to set in. Mood crashes, interpersonal conflict spikes, motivation collapses, sleep disrupts. The horizon feels simultaneously too close and utterly unreachable. Now scale that across not months but generations. In a 400-year voyage at 1% of the speed of light, the third quarter falls somewhere around year 300. The great-great-great-grandchildren of the original crew, living in a ship that is, to them, simply reality, would collectively hit a psychological wall with no cultural preparation for it, no clear end in sight by personal experience, and no way whatsoever to turn back. There is a name that some researchers use for this phase of a generational voyage, the long middle, and it is, by most assessments, the most dangerous part of the journey. Not because of asteroids, not because of radiation, because of what happens when a society loses its sense of purpose and has nowhere to send that loss. This connects to something that the philosopher and bioethicist Konrad Socik has written about in genuine academic literature on generation ships, the problem of the unconsentable passenger. Every person born on that vessel after launch, which in a 400-year voyage means every single person except perhaps the original crew, is there without having chosen to be. They did not consent to this life. They did not agree to be born into a metal cylinder, hurtling through interstellar space, with no exit, no alternative, and no recourse. The mission was decided for them by ancestors based on values and priorities they had no part in shaping. This is not a hypothetical concern. It is a genuine ethical problem that serious scholars are actively debating, and it sits at the center of every credible generation ship proposal. Because the original crew can be selected, trained, psychologically screened, and motivated by genuine personal conviction. But their children cannot, their grandchildren cannot. Their descendants 10 generations removed are simply people born into extraordinary circumstances, carrying the weight of a mission they inherited rather than chose, expected to maintain systems and protocols designed by people dead for centuries based on goals that may or may not still feel meaningful to them. What happens when Generation 37 decides they do not want to go to Proxima Centauri anymore? What happens when a faction within the ship, and factional thinking in isolated groups is well documented, develops a philosophy, a religion, a political identity that rejects the mission entirely, that wants to stop, to simply drift, to build something here in the void, rather than keep chasing a star their ancestors decided mattered? There is no answer to that in any current mission architecture, because no mission architecture can compel the free choices of people not yet born. The physicist and science communicator Cameron Smith at Portland State University, who has published serious academic work on generation ship population genetics, adds another layer to this complexity, and it is one that most people find genuinely surprising. The crew of a generation ship cannot be small. This seems counterintuitive. We imagine a tight-knit group, maybe a few dozen people, resourceful and cohesive. But population genetics tells a different story. A founding population that is too small will suffer from what geneticists call the founder effect, a dramatic reduction in genetic diversity that over generations leads to inbreeding depression, reduced immune function, increased expression of recessive disorders, and a cumulative weakening of the population's biological resilience. Smith's research suggests that a genetically viable founding population, one capable of maintaining sufficient diversity across 400 years without genetic banking or external intervention, would need to be in the range of 14,000 to 40,000 individuals. Other researchers have proposed different numbers, some lower, but the consistent finding is that a crew of dozens or even hundreds is biologically insufficient for the time frame involved. 14,000 people living in a ship for 400 years, that is not a crew, that is a city that must grow enough food, recycle every molecule of water and air, generate its own energy, maintain its own infrastructure, train its own engineers, doctors, teachers, and administrators, resolve its own conflicts, and do all of this without exception, without failure, without a single catastrophic systems collapse for 4 centuries. The engineering requirements alone are staggering. The social ones are almost beyond imagination. Let us talk about food, because it grounds this in something tangible and immediate. A closed ecological life support system, called CELS in the technical literature, is the architecture any generation ship would depend on for nutrition. The concept involves growing food aboard the ship using hydroponics, aeroponics, or other soil-free cultivation methods, cycling nutrients through the system rather than consuming and discarding them, and maintaining a balance of plant species sufficient to provide complete human nutrition across a multi-generational timeline. This sounds manageable in outline. In practice, it is extraordinarily fragile. A single pathogen, a fungal blight, a bacterial infection introduced into a hydroponic bay could devastate a crop species across the entire ship within days. Monocultures, which are far easier to manage at scale, are dramatically more vulnerable to this kind of collapse than diverse agricultural ecosystems. And diverse ecosystems require more space, more expertise, more careful management, resources that are all finite on a sealed vessel. Water is similarly constrained. Every drop must be recaptured and recycled. Humidity from breath and perspiration, urine, wastewater, all of it processed, purified, and returned to the system. The International Space Station does this successfully for its small crew over short durations, but the ISS has regular resupply missions. It has engineers on the ground available for consultation. It has the option in extremis of evacuation. A generation ship has none of those safety nets. Every system must work. Every redundancy must hold. Not for a 6-month mission. For 400 years, some researchers have begun exploring whether the ship might carry frozen genetic material, seeds, embryos, preserved microbial cultures as biological insurance. A kind of vault against ecological collapse to be deployed if a key species is lost. The Svalbard Global Seed Vault on Earth, buried deep in Arctic permafrost, operates on a similar logic for terrestrial agriculture, designing a space-hardy equivalent capable of surviving the radiation environment of interstellar space is one of the more quietly fascinating engineering challenges in this entire enterprise. And then there is energy, the one resource that underlies everything else: life support, propulsion, food production, lighting, communication, computation, medical systems, and the 10,000 other demands of a living, breathing civilization in a box. The energy budget of a generation ship would be immense, and it would have to be sustained without any external source. No solar panels work meaningfully beyond the inner solar system, where sunlight is already negligible, let alone in the interstellar void. The most credible proposals involve nuclear fusion, the same process that powers stars, achieved in a controlled chamber aboard the ship. Fusion offers extraordinary energy density, far beyond any chemical or fission-based system, and its fuel, isotopes of hydrogen, is theoretically available in the interstellar medium itself, but practical, sustained, controlled fusion has been the ambition of human engineering for over 70 years without a fully operational commercial reactor to show for it. The physics is understood. The engineering remains enormously difficult. Achieving fusion is one challenge. Sustaining it continuously for 400 years aboard a vessel with no external maintenance is an entirely different category of problem. Every component ages, every seal wears, every bearing degrades. A generation ship does not simply need systems that work. It needs systems that can be rebuilt from available materials by people who may have lost the institutional knowledge required to understand them multiple times across centuries. There is a thought experiment that does not get nearly enough attention in the generation ship conversation. It goes like this. Imagine you are a child born on the ship. You grow up learning everything the mission requires: basic engineering, biology, agriculture, navigation. You are educated by teachers who were themselves educated by teachers who were educated by teachers who, somewhere back in that chain, actually trained on Earth with real institutions, real laboratories, real accumulated human infrastructure behind them. But each link in that chain is a little thinner than the last. Knowledge, it turns out, does not preserve itself automatically. It requires active transmission. Not just the storage of information, but the cultivation of understanding. There is a profound difference between having a document that describes how to repair a fusion reactor and actually knowing how to repair one. The document can survive centuries in a database. The understanding requires practice, mentorship, repetition, failure, correction. It requires a living tradition of competence, passed deliberately from one generation to the next. And living traditions are fragile things. Anthropologists and historians have documented this pattern repeatedly on Earth, in isolated communities cut off from the broader currents of civilization. Populations stranded on islands, separated from trade routes, cut off from the accumulated knowledge of their parent cultures, have, in documented cases, lost technologies their ancestors possessed, lost the ability to build certain tools, lost agricultural techniques, lost navigational skills, not through laziness or stupidity, but through the quiet, ordinary, invisible process of knowledge dying with the last person who truly understood it before the next generation had fully absorbed it. The formal term for this is cultural loss or skill attrition, and in the context of a generation ship, it is not a distant theoretical risk. It is arguably one of the most probable failure modes of the entire enterprise. Consider what the ship requires its crew to maintain: fusion propulsion systems, closed-loop life support, hydroponic agriculture, radiation shielding integrity, navigation and course correction, medical systems capable of handling everything from childbirth to surgery to epidemic response, structural maintenance of a vessel experiencing continuous stress from acceleration, deceleration, and the slow degradation of materials over centuries, computing infrastructure, communication systems. Even if those communications take years to arrive anywhere, each of these domains on Earth is maintained by entire industries, by universities training specialists, by research institutions continuously refining best practices, by a global network of expertise that any one practitioner can tap into at need. On the ship, every domain must be maintained by a small group of people who have no one outside the hull to call. If the ship's population of trained fusion engineers drops below a critical threshold, through disease, accident, or simply the random variation of how many people in a given generation choose that profession, there may come a point where no one alive fully understands the system keeping them alive. They can follow procedures, they can read manuals, but understanding is not the same as procedure following, and a problem that falls outside the manual requires understanding to solve. Some generation ship proposals attempt to address this with artificial intelligence. If the ship's core systems can be monitored and maintained by sufficiently advanced automated systems, systems capable of diagnosing problems, ordering repairs, and guiding human operators through unfamiliar procedures, then the dependency on transmitted human expertise is reduced. The AI becomes a kind of institutional memory, a repository of understanding that does not age, does not forget, and does not die. This is compelling. It also introduces its own cascade of concerns. An AI system sophisticated enough to manage a generation ship's critical infrastructure across 400 years would need to be extraordinarily robust, not just computationally, but in terms of its values, its goals, and its relationship to the human population it serves. A system that malfunctions, that drifts from its intended behavior, that is modified by successive generations in ways that gradually distort its original purpose, could become something far more dangerous than a knowledge gap. There is also a subtler issue. A population that increasingly depends on an AI system to understand and maintain its own environment gradually loses the capacity to function without it. The human competence atrophies precisely because the AI compensates. And then, if the AI fails, catastrophically suddenly, in a way it cannot self-repair, the crew is left not just without the system, but without the skills the system had replaced. This is not a problem unique to space travel. We navigate versions of it on Earth every time a critical piece of infrastructure becomes so automated that the humans nominally in charge of it no longer truly understand how it works. The difference on a generation ship is that there is no backup civilization waiting to absorb the consequences of a failure. Let us pause here and think about time in a way that is easy to say but hard to actually feel. 400 years ago, the year was 1626. The telescope had been invented less than 20 years earlier. Isaac Newton had not yet been born. The concepts of gravity, electromagnetism, germ theory, evolution, atomic structure, none of them existed in any form recognizable to modern science. The entire framework through which we currently understand the physical universe was completely absent from human thought. The people alive in 1626 were not less intelligent than us. They were not less curious, less creative, less capable of rigorous thought. They simply inhabited a radically different knowledge landscape. A person transported from 1626 to today would find almost nothing familiar in terms of technology, medicine, communication, or scientific vocabulary. Now run that forward. The generation ship launches today, or in 50 years, or in a century. 400 years pass inside the hull. The people who arrive at Proxima Centauri will be as distant from the launch crew, culturally, intellectually, experientially, as we are from the people of 1626. They will have evolved their own language, their own social structures, their own values, their own relationship to the mission and to the stars and to the very concept of humanity. Will they still want to land? Will they even recognize the mission documentation as binding on them? Will they understand the technology well enough to execute an arrival and planetary insertion maneuver designed by engineers who died 3 centuries before them? These are not rhetorical questions. They are genuine engineering and governance problems that no current generation ship proposal has satisfactorily resolved. And the reason they have not been resolved is not a failure of imagination. It is that they may not be solvable in advance. You cannot legislate the decisions of people not yet born. You cannot bind a free society across 4 centuries with a contract signed before any of its members existed. There is a concept in political philosophy called the dead hand problem. It refers to the tendency of past decisions, laws, constitutions, institutional arrangements, property rights, to constrain the freedom of future generations in ways those future generations did not choose and may not endorse. Every society grapples with this tension between the authority of precedent and the autonomy of the living. On a generation ship, the dead hand problem becomes existential. Literally, the mission architecture, the course plotted, the destination chosen, the social structures designed, the resource allocations made, was decided by people who are, by the time it matters most, entirely dead. Every major parameter of the civilization aboard that ship was fixed before the civilization existed. The people living inside it are, in a very real sense, the subjects of a government they never elected, enforcing laws they never ratified, pursuing a goal they never personally chose. How do you build a society that can hold together under those conditions? Some proposals suggest rigid, almost authoritarian governance structures, a mission hierarchy with clearly defined authority, strict protocols for decision-making, and hard limits on individual autonomy in service of collective survival. Critics of this approach note correctly that authoritarian systems in isolated environments have a well-documented tendency toward abuses, fragmentation, and eventual collapse, often violent. Others suggest radical democracy, maximum individual freedom, continuous renegotiation of social norms, fluid governance structures that adapt to the needs of each successive generation. The concern here is coordination. A society that continuously reinvents its own rules may struggle to maintain the institutional consistency required to keep complex technical systems running safely across centuries. The most thoughtful proposals land somewhere in between, trying to design for resilience rather than rigidity, building in mechanisms for adaptation while preserving the core commitments that keep the ship moving and the people alive. But designing for 400 years of social evolution is not like writing a constitution. It is more like trying to predict the weather a year in advance. You can establish general principles, but the specifics will surprise you. Now, I want to bring something into this conversation that rarely appears in the engineering-focused discussions of generation ships, and I think it might be the most important factor of all, meaning. Human beings are not simply biological machines that require food, water, oxygen, and warmth. We are meaning-seeking creatures. We organize our lives around purpose, around the sense that what we do matters, that our efforts contribute to something larger than immediate survival, that there is a reason to get out of bed and face another day in the same enclosed space, with the same people under the same recycled light. The original crew of a generation ship would have meaning in abundance. They chose this, they trained for it, they knew, personally and viscerally, what they were leaving behind and why the destination was worth it. The sacrifice was theirs, made consciously, with full awareness of its weight. Their grandchildren have a different relationship to all of it. The sacrifice was not theirs. The choice was not theirs. The destination is not a dream they carry. It is a data point in a mission document. Proxima Centauri b is not a world they long for. It is a word, a coordinate, a thing their ancestors cared about intensely for reasons that may feel increasingly distant and abstract with each passing generation. Research on communities with strong collective purpose, religious communities, intentional communes, organizations built around a shared mission, shows consistently that meaning can be transmitted across generations. It does not happen automatically. It requires deliberate cultivation, ritual, narrative, ceremony, art, the continuous retelling of the founding story in ways that make it feel alive and relevant to people who did not live it. The generation ship would need, in effect, a culture, a living, breathing, evolving culture that keeps the mission at its center without calcifying into something rigid and coercive. a culture that makes the destination feel real and worth reaching to people who will never see the launch and may never see the arrival. A culture that gives the long middle, those centuries of nothing but void and routine, and the recycled sameness of days, a shape that human beings can inhabit with dignity. Some researchers have proposed that art and music and storytelling are not luxuries on a generation ship. They are structural necessities, as essential to the mission as shielding and propulsion. Because a crew that loses its sense of shared narrative loses its coherence, and a crew that loses its coherence stops maintaining the systems, and a crew that stops maintaining the systems dies. This is not poetic license. This is a genuine argument, made in serious academic papers, that the psychological and cultural architecture of a generation ship is as mission-critical as the physical one. What would the art of a generation ship look like 300 years in? What songs would people sing? What stories would they tell about Earth, a place no living person has ever seen, that exists only in recordings and memories of memories? What would their religion look like if they developed one? What would they believe about the stars, about the destination, about themselves? We cannot know, but we can be certain that whatever they believe, whatever meaning they construct, it will be theirs, not ours. It will have evolved away from the intentions of the founders in ways no one could have predicted, and it will shape every decision they make, including the most consequential one, whether, when they finally arrive at Proxima Centauri after 4 centuries in the dark, they choose to stay. Because there is something waiting at Proxima Centauri that we need to talk about, something the mission planners know, and something that changes the calculus of arrival in ways that are both scientifically fascinating and quietly sobering. Proxima Centauri is not like our Sun. It is a red dwarf, a Class M star, small and cool and dim by stellar standards, burning through its hydrogen so slowly that it will remain on the main sequence for an estimated 4 trillion years. Our Sun, by comparison, has roughly 5 billion years left. Proxima Centauri will be burning long after the Sun has expanded, consumed the inner planets, and faded into a cold white dwarf. In terms of raw longevity, a civilization that successfully established itself around Proxima Centauri would have access to stellar energy on a timescale that dwarfs anything our own solar system can offer. Let us talk about what the crew would actually be flying toward. Because for all the extraordinary difficulty of the journey itself, the radiation, the psychology, the generational drift, the slow erosion of knowledge and purpose, there is a possibility that the hardest part of this entire enterprise is not the 400 years of crossing. It is the moment of arrival. The moment the descendants of the original crew finally decelerate into the Proxima Centauri system and get their first real close look at the world their ancestors died believing in. Because Proxima Centauri b, that rocky, potentially habitable planet orbiting our nearest stellar neighbor, exists in a relationship with its star that is almost nothing like the one Earth enjoys with the Sun. And understanding that relationship requires understanding what kind of star Proxima Centauri actually is, at a level deeper than its classification suggests. A red dwarf star like Proxima Centauri is in many ways a paradox. It is simultaneously the most common type of star in the galaxy. Roughly 70% of all stars are red dwarfs, and the type of star least like what we instinctively imagine when we think of a star. It is small. Proxima Centauri has a mass of approximately 12% of our Sun's mass, and a radius of about 15% of the Sun's radius. If you placed it where our Sun sits, it would span a fraction of the sky that the Sun currently occupies. Its surface temperature is around 3,000 degrees Celsius, compared to our Sun's roughly 5,500 degrees Celsius. It glows with a deep reddish-orange hue, dim and cool and ancient feeling, even though it has barely begun its stellar life by any meaningful measure. and because it is so small and so cool, any planet within its habitable zone, the orbital distance at which liquid water could theoretically exist on a surface, must orbit extraordinarily close to it. Proxima Centauri b, our candidate world, sits at a distance of roughly 0.049 astronomical units from its star. For comparison, Mercury, the innermost planet of our solar system, orbits at about 0.39 astronomical units from the Sun. Proxima Centauri b is nearly 8 times closer to its star than Mercury is to ours. That proximity has consequences, profound, civilization-shaping, potentially life-ending consequences. The first and most discussed consequence is tidal locking. At such a close orbital distance, the gravitational interaction between Proxima Centauri and its planet is expected to have, over geological time, synchronized the planet's rotation with its orbital period. This is the same process that locked our moon's rotation to its orbit around Earth, which is why we always see the same face of the moon. Proxima Centauri b almost certainly shows one face permanently to its star and the other face permanently to the cold of space. Think about what that means for a world. The day side, the hemisphere facing the star, receives continuous stellar radiation, no day and night cycle, no sunrise or sunset, just a dim reddish star hanging motionless in the sky, bathing the surface in a permanent unvarying glow. Temperatures there could be extreme, though models vary widely on precisely how extreme, depending heavily on whether the planet has an atmosphere and how that atmosphere circulates heat. The night side, meanwhile, faces the void. Permanently, with no stellar input whatsoever, temperatures could plunge to extraordinarily low levels, cold enough, in the absence of atmospheric heat transport, to freeze out entire atmospheric constituents, potentially causing what scientists call atmospheric collapse. If the atmosphere freezes onto the night side surface, the day side is left exposed, a bare rock under a dim star, with nothing between it and the radiation environment of space. Whether atmospheric collapse actually occurs on Proxima Centauri b depends on complex factors. The thickness and composition of any atmosphere, the efficiency of circulation between hemispheres, the presence of oceans or other heat reservoirs. Some climate models suggest that a sufficiently thick atmosphere could redistribute heat effectively enough to moderate both hemispheres into potentially habitable ranges. Others are more pessimistic. The honest answer is that we do not know. We genuinely, with our current instruments and models, cannot determine with certainty what the surface conditions on Proxima Centauri b are like, and the crew of the generation ship would be flying toward that uncertainty with no ability to turn back. But tidal locking, significant as it is not the most immediately dangerous feature of Proxima Centauri. That distinction belongs to something far more violent. Flares. Proxima Centauri is a flare star. This is not a rare, unusual designation for red dwarfs. In fact, flaring activity is essentially a standard feature of the type, but the magnitude and frequency of Proxima Centauri's flares are striking even by red dwarf standards. In 2016, the same year Proxima Centauri b was announced, astronomers recorded a flare from Proxima Centauri that increased the star's brightness by a factor of approximately 68 over its normal output in the ultraviolet portion of the spectrum. This happened over the course of just a few minutes. Then, in 2019, a study led by Meredith McGregor at the University of Colorado Boulder, using data from multiple observatories including ALMA, the Atacama Large Millimeter Array, recorded what they described as one of the most powerful stellar flares ever observed from Proxima Centauri. The flare released approximately 100 times more energy than any solar flare ever recorded from our own Sun, and it lasted for approximately 100 seconds. The most energetic flare ever recorded from our Sun, multiplied by 100, compressed into less than 2 minutes. Now recall that Proxima Centauri b orbits at a fraction of the distance that Earth orbits our Sun. The planet sits roughly 8 times closer to its star than Mercury sits to ours. When a flare of that magnitude erupts from Proxima Centauri, the planet receives a dose of high-energy radiation, X-rays and extreme ultraviolet radiation that would be orders of magnitude beyond anything Earth experiences during even the most intense solar storm events. On Earth, our atmosphere and magnetic field absorb and deflect the vast majority of this radiation before it reaches the surface. Life as we know it depends on those shields. Strip them away, and the radiation environment becomes lethal to surface life with the biological machinery we are familiar with. Whether Proxima Centauri b has a magnetic field capable of providing meaningful protection is one of the central open questions in exoplanet science. The answer depends on the planet's interior structure, its rotation rate, which, if tidally locked, is very slow, and its geological history. Tidal locking significantly reduces the likelihood of a strong planetary magnetic field, because magnetic field generation in rocky planets is generally associated with a rapidly spinning, partially molten iron core, a world that rotates only once per orbital period, every 11 Earth days, may generate a dramatically weaker magnetic field than Earth does. Without a strong magnetic field, without meaningful atmospheric shielding, the surface of Proxima Centauri b may be continuously scoured by ultraviolet and X-ray radiation from its host star, not occasionally during unusual events, but routinely, as a baseline feature of its environment. A 2017 study published in the Astrophysical Journal, led by researchers at the University of Exeter, modeled the atmospheric erosion of Proxima Centauri b under realistic stellar wind conditions. Their results suggested that the planet's atmosphere, if it ever had one, could have been substantially or entirely stripped away by the combined effect of stellar wind pressure and flare events over geological time. The stellar wind from Proxima Centauri, despite the star's small size, is estimated to be between 1,000 and 2,000 times more intense at the orbital distance of Proxima Centauri b than the solar wind is at Earth's orbital distance. A wind that's strong, sustained over billions of years, does not just erode an atmosphere, it sculpts the entire history of a world. It determines whether oceans can form and persist, whether chemistry complex enough for biology can develop and survive, whether the surface looks anything like what the Generation ship's crew, raised on mission documents written by Earthbound scientists, might be expecting. The crew arrives, they decelerate into the system, they point every instrument they have at the planet their entire civilization was built to reach, and the data comes back. What does it say? We do not know, and that uncertainty, genuine, unresolved, acknowledged by the scientist actively working on this, is not a failure of science. It is science working exactly as it should. The limits of our current knowledge are clearly marked. The questions are well defined. The answers are waiting, either for better telescopes or for whoever actually makes that journey. The James Webb Space Telescope, launched in December of 2021, and now operating at its observational station, roughly 1.5 million kilometers from Earth, has already begun transforming our understanding of exoplanet atmospheres. Its infrared sensitivity allows it to detect the chemical signatures of atmospheres around distant worlds, not Proxima Centauri b directly, because that planet does not transit its star from our viewing angle, making atmospheric spectroscopy extremely difficult, but for other worlds in comparable situations around red dwarfs. The TRAPPIST-1 system, discovered in 2017 and located approximately 40 light-years from Earth, contains 7 rocky planets, several of which orbit within the habitable zone of their red dwarf host star. Webb has already delivered preliminary data on the atmospheres of some of these worlds. Early results have been sobering in some respects. One inner planet appears to lack any substantial atmosphere, but the science is young and the instruments are still learning the system. Every observation adds a piece to a picture that is, planet by planet, slowly coming into focus. What Webb learns about the TRAPPIST-1 worlds will directly inform our expectations for Proxima Centauri b. They are not identical situations, no two exoplanets are, but they are close enough analogues to be genuinely instructive. The red dwarf habitability question, which seemed almost purely speculative just a decade ago, is now being answered with real data from real telescopes pointed at real worlds. The generation ship's crew, arriving 400 years from now, would have answers we currently do not. They would know from their own instruments whether an atmosphere exists, whether it is breathable or toxic or absent, whether the surface holds liquid water or frozen plains or bare irradiated rock, whether the world is a gift or a graveyard, and they would have to make the decision about what to do next entirely on their own. Because any message sent back to Earth, seeking guidance, would take 4.24 years to arrive. The reply would take another 4.24 years to return. For every question the crew sends home, they wait nearly 9 years for an answer. In a situation requiring immediate decision-making, and planetary arrival almost certainly would, they are, for all meaningful purposes, alone. Let us consider the scenario where the arrival data is unfavorable, where Proxima Centauri b turns out to be uninhabitable, stripped of atmosphere, scorched by flares, geologically dead, or otherwise incompatible with human settlement. This is not an unlikely outcome. It is, arguably, one of the more probable ones given what we currently understand about the radiation environment. What then? The generation ship has consumed its entire civilization, 400 years of human life, sacrifice, birth and death, cultural evolution and institutional struggle to reach this point. The ship itself may be aging beyond reliable function. The propulsion systems have been running for centuries. The population may be significantly smaller than the founding generation, or significantly larger, depending on how well the demographic management worked. Resources are not unlimited. There are a small number of options, none of them easy. 1. Attempt settlement anyway, not on the planetary surface, but in orbit, building a permanent space habitat around Proxima Centauri rather than landing on its planet. This preserves the general destination while abandoning the specific dream of a terrestrial home. It requires the construction of a habitat that does not currently exist from materials that would need to be extracted from local asteroids or other bodies in the system by a crew whose manufacturing capacity was designed for survival and transit, not large-scale construction. 2. Explore the system for alternative settlement sites. Proxima Centauri has at least one other candidate planet, Proxima Centauri d, a much smaller world orbiting even closer to the star, announced in 2022. Neither is obviously better than Proxima Centauri b for surface habitation, but the system may contain other bodies, large moons, asteroid belts, objects not yet catalogued from Earth, that could offer resources or opportunities. 3. Turn around. Attempt to return to the solar system, which is now 4.24 light-years behind them, requiring another multi-century voyage, with a ship that has already spent centuries in transit and a population that has never known any home except this one. None of these are good options. All of them represent a version of the mission succeeding at the journey and failing at the destination, and all of them would fall to the descendants of the founders, people who inherited this situation rather than chose it. To navigate, there is something quietly profound about all of this when you step back from the engineering and the biology and the stellar physics and simply sit with the human reality of it. A group of people, real people, with names and faces and inner lives as rich and complicated as yours, climb into a vessel and leave. They leave knowing they will never return. They leave knowing they will die in transit, that their children will die in transit, that the generation ship will become not a vehicle but a world in motion, hurtling through the dark, carrying everything that matters about the people inside it. 400 years pass. The universe goes on around the ship without caring. Stars are born and die in distant corners of the galaxy. Civilizations on Earth rise and change and transform in ways that would be unrecognizable to anyone aboard. Technology advances. Perhaps the problems of interstellar travel are solved by some new physics discovered after the ship launched, and sleek, fast vessels overtake the generation ship decades before its arrival, the passengers living inside a vehicle that history rendered obsolete while they were still in transit. That has actually been proposed as a genuine concern by theorists thinking about the timing of a generation ship launch. If you send a slow ship now and the technology improves dramatically afterward, the slow ship might be overtaken. Its crew might arrive to find people who left Earth centuries later already waiting for them, having made the journey in a fraction of the time. The emotional weight of that scenario, the sheer existential strangeness of it, is difficult to fully articulate. And yet, the ship was sent. The people inside it lived their lives. They loved each other, argued with each other, created art and music and meaning in a cylinder of metal moving through the deepest dark. They were real. Their lives were real. The cosmos did not diminish them simply because the universe moved faster than they did. That is the thing about this journey that I find most moving when I sit with it long enough. Here is a problem that sounds simple until you actually think about it. You are moving at 1% of the speed of light, or 5%, or whatever fraction of that enormous velocity your propulsion system managed to achieve during the acceleration phase of the journey. You have been moving at this speed for decades, possibly centuries. The ship is massive, tens of thousands of tons of hull, machinery, water, soil, people, and everything a civilization needs to survive. And now, ahead of you, growing slowly brighter in the instruments, is Proxima Centauri. You need to stop, not stop completely. You need to match orbital velocities with the system, slow to a speed that allows controlled navigation within it, rather than rocketing through it like a stone thrown across a pond. But the physics of deceleration at interstellar velocities is not like applying brakes. There are no brakes. There is no friction. There is nothing to push against except the reaction mass your propulsion system can expel, and you have been consuming that reaction mass for the entire journey. This is, without exaggeration, one of the most difficult unsolved engineering problems in the entire generation ship concept. And the way researchers have approached it reveals something genuinely beautiful about the relationship between physics and imagination. To understand why deceleration is so hard, you need to understand what it costs. Every rocket, every propulsion system based on expelling mass in one direction to move in the other, is governed by something called the Tsiolkovsky rocket equation, formulated by the Russian mathematician Konstantin Tsiolkovsky in 1897. The equation describes the relationship between a rocket's change in velocity, the velocity at which it expels propellant, and the ratio of its initial mass to its final mass after the propellant is consumed. The brutal implication of this equation is that the propellant required grows exponentially with the desired velocity change. To accelerate a large ship to 1% of the speed of light, you need an enormous amount of propellant. To then decelerate that same ship back to near zero velocity at the destination, you need another enormous amount of propellant on top of that. Propellant that you had to carry with you through the entire journey, which itself required more propellant to accelerate, which required more propellant to carry, which required more propellant to accelerate that additional propellant the mathematics spiral into absurdity quickly. For chemical rockets, the required propellant mass for an interstellar voyage would be so astronomically large as to be physically meaningless. Even for fusion propulsion, the most credible high-energy option currently discussed, the propellant requirements for a full acceleration and deceleration mission profile are staggering. This is why some of the most creative engineering proposals separate the acceleration phase from the deceleration phase entirely. You use powerful propulsion to accelerate the ship before it leaves the solar system, perhaps with laser arrays, perhaps with a mass driver, perhaps with a powerful onboard drive during the early years of flight, and then you rely on something else entirely to slow down at the other end. The most elegant deceleration concept currently in serious discussion is called magnetic braking, or more specifically, magnetic sail deceleration. The idea was developed and refined over several decades, with significant contributions from the physicist Dana Andrews and the engineer Robert Zubrin in the early 1990s. Here is how it works. As the ship enters the Proxima Centauri system, it deploys an enormous superconducting loop, a vast ring of wire carrying a persistent electrical current, creating a powerful magnetic field that extends far beyond the physical structure of the ship itself. This artificial magnetosphere interacts with the stellar wind of Proxima Centauri, the continuous stream of charged particles the star emits in all directions, in a way that creates drag, real, measurable, physics-based drag. The stellar wind pushes against the magnetic field, and the field pushes back against the ship, slowing it down. The deceleration is gentle by the standards of chemical rockets. It would take years, not hours, but it requires no onboard propellant. The energy doing the work comes from the star itself, from the stellar wind that Proxima Centauri has been emitting for billions of years and will continue emitting long after the ship arrives. The ship essentially sails against the wind to slow down, the way a boat might tack against the wind on water. There is something almost poetic about this. A vessel that crossed 4 light-years of interstellar void, using the energy of our sun to launch, using the energy of a distant star to stop. 2 stars, separated by 40 trillion kilometers, cooperating across the gulf to carry a fragment of life from one to the other. The engineering challenges are significant. Superconducting loops of the required size do not currently exist, and maintaining superconductivity in the radiation environment of interstellar space requires material science well beyond our current capabilities. But the physics is sound. The concept works, in principle, and that matters. There is another deceleration concept worth discussing, and it is considerably more speculative, but no less fascinating. It involves using the interstellar medium itself as a brake. As the ship moves through the diffuse gas and dust between stars, the forward hull experiences a continuous, if extremely gentle, pressure from particle impacts. At cruise velocity, this is primarily a radiation hazard, as we discussed earlier. But in the later stages of deceleration, when the ship is already slowing and the interaction cross-section can be increased, some proposals suggest deploying a vast forward-facing sail or electromagnetic field that maximizes this interaction, turning the interstellar medium from a passive obstacle into an active braking mechanism. The density of the interstellar medium is so low, roughly 1 atom per cubic centimeter, sometimes far less, that this approach would require either a truly enormous effective cross-section or a very long time to achieve meaningful deceleration. But in a mission already measured in centuries, a slow deceleration is not necessarily a problem. It is simply a parameter to plan around. What makes this concept interesting beyond its engineering specifics is what it represents conceptually. The interstellar medium, that vast, cold, seemingly hostile emptiness between stars, becomes a resource, something to work with rather than simply endure. The void is not just a barrier to cross. It is a medium to navigate, in the same way that sailors learn to read the ocean not as an obstacle but as a working environment. Now let us think about what deceleration actually feels like from inside the ship, because this is where the human story gets interesting again. For most of the voyage, the long cruise phase, after initial acceleration and before final deceleration, the ship is in free fall. It is not accelerating or decelerating. From the perspective of the people inside, there is no up or down, no gravity. The ship must be designed to handle this, either through continuous rotation to simulate gravity, a concept that has been part of space station design thinking since the earliest days of the space age, or through accepting the biological consequences of long-duration microgravity exposure, which are severe and well documented. On the International Space Station, astronauts experience significant bone density loss, muscle atrophy, cardiovascular changes, and fluid redistribution during missions of 6 months to a year. These effects are mitigated through intensive daily exercise regimes and careful medical monitoring. For a generation ship cruise phase lasting decades or centuries, the same physiological pressures would apply, but at a scale that exercise alone may not adequately address. Rotational gravity is the most credible solution. A ship section rotating at a rate that generates a centripetal acceleration equivalent to 1 standard gravity would prevent the worst musculoskeletal and cardiovascular deconditioning. The required rotation rate depends on the radius of the rotating section. Larger radius means slower rotation needed for the same effective gravity, and slower rotation is more comfortable for the human vestibular system, which struggles with rotation rates above approximately 2 revolutions per minute. A comfortable rotational habitat would need to be quite large, on the order of several hundred meters in radius, which is itself an engineering constraint that shapes the entire vessel architecture. When deceleration begins, the ship's drive fires in the direction of travel, pushing against the direction of motion to slow down. This means the thrust now comes from the front of the ship rather than the rear. If the crew had oriented their living quarters around the acceleration phase, using engine thrust as their artificial gravity, they now need to physically invert their sense of up and down. The floor becomes the ceiling becomes the floor. This transition from acceleration gravity to cruise phase weightlessness to deceleration gravity running in reverse is one of the more disorienting aspects of the journey that rarely gets discussed. For generations born during the cruise phase, who grew up in a rotating habitat with no lived experience of a thrust gravity floor, the deceleration phase would introduce a type of sensation their bodies and inner ears have never encountered. The entire physical relationship between the crew and their vessel would shift. Let us talk about communication across this journey, because it shapes the psychological experience of the voyage in ways that go beyond the technical. From the moment the ship clears the inner solar system and begins its transit, every communication with Earth is delayed by the finite speed of light. In the early years of the journey, within the first few light months, the delay is noticeable but manageable. A message sent home takes hours or days to arrive. The reply takes hours or days to return. Conversations become asynchronous. Real-time interaction disappears. This is already the situation for Mars missions, and space agencies have developed protocols for handling it. But as the ship moves further out, the delay grows. By the time the vessel has traveled 1 light-year, roughly 1/4 of the way to Proxima Centauri, every message home takes a year to arrive. The reply takes another year. The crew is having conversations with Earth that span 2 years per exchange. The people they are talking to on the other end are not the same people who sent the previous message. The world has changed. The agencies that launched them may have changed governments' priorities, or ceased to exist in the form that sent the ship, by the midpoint of the journey, 2 light years out. The delay is 2 years each way, 4 years per exchange. A crew member who sends a message at age 30 will receive the reply at age 34 if a reply is sent immediately. Their children, born in transit, may have grown up enough to read the response themselves before it arrives. This progressive disconnection from Earth is not just a communication inconvenience, it is a fundamental psychological shift. The ship moves from being a remote outpost of human civilization in continuous if delayed contact with home to being genuinely independent, an autonomous world that happens to send and receive occasional dispatches from a place that recedes further and further into the past. At some point in the journey, a threshold is crossed. Not a physical one, just a psychological and cultural one. Earth stops being home, the ship is home, and the people inside it are no longer travelers from somewhere else. They are simply themselves, living in the only world they have. There is something that happens to the night sky during this journey that I want to describe carefully, because it captures something profound about the nature of this voyage. In the early years of transit, the constellations still look familiar, slightly distorted by the ship's velocity, the relativistic aberration we discussed earlier, but recognizable. Orion is still Orion, the Southern Cross is still the Southern Cross. The patterns that human beings have named and navigated by for tens of thousands of years are still there, rearranged slightly but present. As the ship approaches the halfway point, something subtle but cumulative has happened to the sky. The constellations have drifted. The apparent positions of stars have shifted not just because of relativistic effects, but because the ship has physically moved 4.24 light-years, more than 40 trillion kilometers, from its starting point. Stars at different distances from the ship shift by different amounts as the viewing angle changes. This is the same effect, called stellar parallax, that astronomers use to measure the distances to nearby stars from Earth. But from interstellar distances, the effect is not a tiny wobble measured in thousandths of an arc-second. It is a dramatic reshaping of the entire sky. By the time the ship reaches Proxima Centauri, the constellations that human beings have called by the same names for all of recorded history will be unrecognizable. Orion's stars, spread across hundreds of light-years of space, will have separated and recombined into entirely different patterns when seen from 4 light-years away. The Big Dipper will not exist. The familiar shapes, the mythological figures, the navigational anchors that have oriented humans since before writing will be gone. An astronomer born on the ship would look at the sky and see a universe that no earthly star chart describes. They would be the first human beings in history to witness the cosmos from outside the solar neighborhood, the first to see the sky from truly alien ground, and in the center of that rearranged sky, growing slowly brighter as the ship decelerates, would be the destination. No longer a point of reddish light indistinguishable from its neighbors, now a distinct small warm ember hanging in the dark, growing, resolving, becoming real in a way that no mission document, no recording, no archived testimony from a founding crew member could have made it feel. The star that 400 years of human civilization lived and died to reach. Finally, undeniably there. There is a moment I keep returning to when I think about this journey. Not the launch, not the arrival. A quieter moment, somewhere in the middle. It is several generations into the voyage. The ship is running smoothly, or at least as smoothly as a 4-century mission ever runs. A child, maybe 10 or 11 years old, is sitting near one of the viewports, looking out. The stars are perfectly still, perfectly sharp, burning in the absolute silence of the void with a clarity that no earthly atmosphere ever permitted. This child has never seen rain, has never felt wind on their face, has never heard an animal, or watched a river, or stood on ground that did not have machinery humming underneath it. Earth is a story their grandparents told. Proxima Centauri is a story their parents will tell. Neither is real in the way the ship is real, but the stars are real, undeniably, intimately, overwhelmingly real. And this child, born in the void, raised in the dark, knowing no sky except this one, looks at them and feels something. Something that has no name in any language yet invented, because no human being has ever been in exactly this position before. That feeling, whatever it is, might be the truest thing about this entire endeavor. The most honest answer to why any civilization would attempt it at all, not because the destination is certain, not because survival is guaranteed, not because the math works out cleanly, but because looking at the stars and feeling pulled toward them is one of the oldest and most persistent things about being human. And some version of that feeling, carried across 400 years and 40 trillion kilometers, burning quietly in a child's chest at a viewport in the interstellar dark, would still be recognizable, still be ours. If you are enjoying this journey, make sure to give this video a like and subscribe. You will be part of a community that explores the cosmos together. In 2022, a team of astronomers published a paper that quietly rewrote the Proxima Centauri mission brief in ways that had not been fully anticipated. We had known about Proxima Centauri b since 2016, that rocky, potentially habitable world orbiting inside the star's habitable zone, the one that transformed Proxima Centauri from an interesting stellar neighbor into a destination with an address. For several years, it was the centerpiece of every serious discussion about interstellar travel, the world we were going to, the reason to build the ship. Then the data from additional radial velocity measurements came in, and astronomers announced the detection of a second planet, Proxima Centauri d, a sub-Earth mass world, potentially as light as 1/4 of Earth's mass, orbiting even closer to the star than Proxima Centauri b, at a distance of roughly 0.029 astronomical units, and completing a full orbit in just 5 Earth days. It is one of the lowest mass exoplanets ever detected using the radial velocity method, which measures the tiny gravitational wobble a planet induces in its host star. Detecting something that's small, that close to a dim red star at 4.24 light-years of distance, using instruments on the surface of Earth, that is a measurement so precise it borders on the philosophically uncomfortable. And it means the Proxima Centauri system is not a single planet destination. It is a system, a place with architecture, with multiple worlds, with complexity we had not fully appreciated until we looked harder. The significance of this for a generation ship mission is layered. On one level, it is encouraging. A system with multiple planets is more likely to contain useful resources, asteroids, rocky bodies, volatile rich objects that an arriving civilization could exploit for raw materials, fuel, and potentially habitat construction. A single planet with hostile surface conditions is a dead end. A system with multiple bodies offers options, fallback positions, room for creative problem solving. On another level, it complicates the mission in ways that require careful thought. The mission was designed, in whatever planning documents the founders created, in whatever goals were encoded into the ship's institutional memory around a specific destination. Proxima Centauri b, the habitable zone planet, the candidate world. But if the crew arrives and finds that Proxima Centauri b is uninhabitable, the presence of Proxima Centauri d does not automatically solve the problem. Proxima Centauri d orbits even closer to a flare star than Proxima Centauri b does. Its radiation environment is almost certainly more intense. Its prospects for surface habitability are, by most assessments, lower. But here is what makes this genuinely interesting, rather than simply discouraging. We do not yet know whether there are more planets in this system. The radial velocity method, powerful as it is, has detection limits. It finds planets most easily when they are massive and close to their star, because massive close-in planets create larger stellar wobbles that are easier to measure. Smaller planets, further out in longer orbital periods, are much harder to detect with current instruments. The Proxima Centauri system may contain planets we have not yet found. Worlds further from the star in cooler orbits with longer years, potentially with entirely different surface environments. We simply do not know. And the generation ship crew, arriving with instruments far more sensitive than anything we can currently build, instruments evolved over 4 centuries of scientific progress, would have the ability to survey the system with a thoroughness impossible from Earth. They might find something we missed, something that changes everything. There is also a third body in the Proxima Centauri system that deserves attention, because it is frequently overlooked in discussions of the destination, and yet it has profound implications for any arriving civilization. Proxima Centauri itself is almost certainly gravitationally bound to the Alpha Centauri binary system. The 2 Sun-like stars, Alpha Centauri A and Alpha Centauri B, that together with Proxima form what is collectively called the Alpha Centauri system. The 3 stars orbit a common center of mass, with Proxima sitting at an enormous distance from the binary pair, roughly 13,000 astronomical units away on its current orbital trajectory. At that separation, a full orbit of Proxima around the Alpha Centauri binary takes somewhere in the range of 500,000 years. From the surface of any world orbiting Proxima Centauri, the Alpha Centauri binary would be visible as 2 extraordinarily bright stars, far brighter than any other stars in the sky, though still appearing as points of light rather than disks to the naked eye. They would be among the most luminous objects visible from that system, a constant reminder that this stellar neighborhood is not just 1 star but 3, and Alpha Centauri A and B are individually Sun-like stars. Alpha Centauri A is slightly larger and more luminous than our Sun. Alpha Centauri B is slightly smaller and dimmer. Both are within the range of stellar types considered broadly amenable to planetary habitability around them. Whether either host's planet remains an active area of investigation, the proximity of the binary pair to each other creates complex gravitational dynamics that constrain where stable planetary orbits can exist. But the question is not closed. For a generation ship civilization that has arrived at Proxima Centauri and found its planets less hospitable than hoped, the Alpha Centauri binary sitting roughly 0.2 light-years away, a tiny fraction of the distance already traveled, represents something remarkable, a potential next step, not a destination requiring another 400-year voyage, but a nearby stellar neighborhood accessible, in principle, to a civilization that already has interstellar-capable technology and has done it once before. This is where I want to slow down for a moment and sit with something that I think gets lost in the engineering-heavy conversations about generation ships. We talk about Proxima Centauri B as though it is the point, the goal, the justification for everything. 400 years of sacrifice aimed at a specific coordinate in space, a specific world around a specific star. But the generation ship, if it ever launches and ever arrives, would represent something far more significant than the delivery of a population to a destination. It would represent the moment humanity became an interstellar species. Not metaphorically, not aspirationally, actually physically, in hard material reality, a civilization with members living and thriving around more than 1 star, with children being born under a sky lit by a different sun than the one that warmed every ancestor they ever had, with a lived, embodied knowledge of what interstellar space looks and feels and smells and sounds like from the inside. That knowledge, that experience, would be irreversible. It could not be undiscovered. It could not be taken back. The universe, which for the entire 4 billion-year history of life on Earth had been something observed from a single point, would have been entered, explored, inhabited. Every civilization in human history has been defined by the edges of its world, by the boundaries of what it could reach, by the horizon beyond which lay the unknown. The generation ship does not just move the horizon, it eliminates the concept of a final horizon altogether. If you can cross 4 light years, the question immediately becomes, what about 8? What about 40? What about 400? The first generation ship, if it ever flies, will not be the last. Now, and I want to be honest, that this next section ventures into territory where the science is genuinely uncertain and actively debated. Let us talk about something that the crew of a generation ship would almost certainly spend considerable time thinking about during that long, dark crossing. Are they alone? The Fermi paradox, the famous tension between the apparent likelihood of extraterrestrial civilizations existing somewhere in the universe and the complete absence of any detected signal or evidence of them, sits quietly underneath every interstellar travel discussion. If the universe is as vast and ancient as we know it to be, and if the conditions for life arise as readily as some estimates suggest, then the silence of the cosmos requires an explanation. Where is everyone? The generation ship crew, crossing the void in their metal world, would have a peculiar and intimate relationship with this question. They would be living proof that the crossing is possible, that biology can survive interstellar distances, that civilization can maintain itself across the gulf, that the barriers to interstellar travel are real but not absolute. They would be, in a sense, the answer to their own version of the Fermi question. They exist, they crossed, therefore it is possible. But Proxima Centauri is the closest star to our own. If any other civilization had ever done what the generation ship crew is doing, crossed the interstellar void, established itself around another star, expanded outward, the evidence of that expansion should, over millions of years, have propagated across the entire galaxy. The galaxy is old enough, and the distances involved, even at modest interstellar travel speeds, short enough on cosmic timescales, that a civilization that began expanding even 1 million years ago would have had time to reach every star in the Milky Way many times over. And yet, silence, no signals, no megastructures, no evidence of reshaping on the scales a truly advanced technological civilization might produce. Just stars and gas and the quiet hum of a universe going about its business without any obvious signs of company. The generation ship crew would cross the void and arrive at Proxima Centauri and find, almost certainly, an empty system. No signals, no artifacts, no indication that anyone else had been there before. The first visitors, or possibly among the first visitors in the history of the galaxy. That silence, experienced not from a comfortable distance through a radio telescope on Earth, but from inside the destination system, surrounded by the dim light of a red dwarf star with 4 light-years of void between them and the nearest other human beings. That silence would be a different thing, more intimate, more present, more honest. I want to mention something here that connects the scale of what we are discussing to something you can actually do tonight, or any clear night you happen to find yourself under a dark sky. Everything we have talked about in this video, Proxima Centauri, the Alpha Centauri system, the red dwarf stars, the candidate worlds orbiting them, all of it is visible from the southern hemisphere with the naked eye, and in more detail than most people realize. Alpha Centauri, the bright binary system gravitationally linked to Proxima, is the 3rd brightest star system in the entire night sky. It is not a distant abstraction available only to professional telescopes. It is right there, burning steadily above the southern horizon on a clear night, a point of warm golden light that your own eyes can find without any equipment at all. But there is a difference between finding a point of light and actually seeing a star system. Through even a modest telescope, Alpha Centauri resolves into two distinct stars, A and B separated into individual points, each with its own color and brightness. You are no longer looking at a coordinate. You are looking at suns, real, physical, ancient nuclear furnaces sitting 4.24 light-years away, with their own planetary systems potentially orbiting them, in a stellar neighborhood that a future generation ship might one day call home. The Celestron StarSense Explorer, the telescope I mentioned earlier in this video, will find Alpha Centauri for you automatically, using your phone to map the sky in real time. But more than that, it will find the objects that put this entire journey in context: the Eta Carinae Nebula, the Jewel Box Cluster, the Coal Sack, the dark molecular cloud that would absorb starlight as a generation ship passed through the galactic plane. These are not images on a screen. They are photons that have traveled thousands of light years and are landing right now on your retina. That is a different experience from watching a documentary, and I think it matters. The link is in the description and pinned on the comments if you want to explore it. Now back to the ship, back to the silence, and back to a question that the crew, sitting in orbit around a dim red star at the edge of everything familiar, would almost certainly ask themselves, what do we do now? Because arrival is not the end of the story. It is the beginning of a different one. And the decisions made in those first months and years after deceleration, before anyone sets foot on any surface, before any permanent structure is built, before the ship transitions from a vessel in motion to a habitat in orbit, those decisions would shape everything that follows. The first task would almost certainly be survey. Comprehensive, meticulous, instrument-intensive mapping of the entire system. Every planet, every moon, every significant asteroid, every detectable source of water ice or volatile chemicals or useful minerals. The crew would know more about the Proxima Centauri system from the vantage point of orbit than Earth-based astronomers will know for decades or centuries to come. They would see the planet's surface directly, measure its atmospheric composition, if an atmosphere exists, detect geological activity or its absence, map magnetic field strength and topology, assess radiation flux at the surface under typical and flare conditions. This survey phase, which realistically could take years, would be the most scientifically extraordinary period in the history of human exploration. Every measurement would be a first. Every data point would answer a question that humanity had been asking since the discovery of exoplanets. And the crew, descendants of people who left Earth 400 years ago, raised in a metal world, shaped by centuries of cultural evolution inside the ship, would be the ones making those measurements, their instruments, their eyes, their decisions about what to look for and how to interpret what they find. That is a thought that stays with me. 400 years of human sacrifice arriving at a moment of pure discovery. Whatever they find, habitable world or barren rock, rich system or sparse emptiness, the finding itself would be one of the greatest moments in the history of our species. And we would know about it, eventually, 4 years and 3 months after they sent the signal. Give or take, the message would arrive at Earth, or whatever Earth has become by then, at the speed of light, crossing the same void the ship spent centuries crossing in just 4 years. Let us start with something that sounds almost too strange to be real science. Your DNA, the roughly 3 billion base pairs coiled inside virtually every cell in your body, the molecular instruction set that makes you specifically you, is not a static document. It does not sit unchanged from the moment of conception, faithfully copied from cell to cell, generation to generation, without alteration. It is more dynamic than that, more responsive, more alive in a sense than the word code usually implies. Wrapped around that DNA, interacting with it continuously, is a second layer of biological information called the epigenome, The epigenome does not change the DNA sequence itself. The letters of the genetic code remain what they are, but it determines which genes are active and which are silenced, which instructions are read and which are ignored. It is, in the most useful metaphor available, the difference between the full text of a book and the passages someone has highlighted, annotated, and dog-eared based on their specific experience of reading it. And unlike the DNA sequence, the epigenome changes in response to the environment, to stress, to diet, to toxin exposure, to radiation, to social conditions, to the quality of sleep and the experience of trauma and the accumulated texture of a life lived in particular circumstances. Some of those changes can be inherited, not permanently, not inevitably, but under certain conditions. Epigenetic modifications acquired during a parent's lifetime can be passed to their children. This is called transgenerational epigenetic inheritance, and it is one of the most actively researched and genuinely surprising frontiers in modern biology. Now put that biology on a generation ship. The environment inside a generation ship is radically different from anything human biology evolved to handle. The radiation exposure, even with shielding, is higher than on Earth's surface, particularly from galactic cosmic rays that no practical shielding can fully stop. The light is artificial, calibrated to approximate a 24-hour cycle, but never quite matching the full spectral complexity of actual sunlight filtering through an actual atmosphere. The food is hydroponically grown, nutritionally engineered, but lacking the microbial diversity of soil-grown produce and the ecological complexity of a real food web. The social environment is unprecedented, a fixed population in a fixed space with no immigration, no external cultural input, no possibility of leaving. Each of these factors exerts pressure on the epigenome, not catastrophically, not overnight, but continuously, cumulatively, across decades and then generations. The epigenetic patterns of someone born and raised on the ship would be measurably different from those of the founding crew, and their children's patterns would differ further, and their grandchildren's further still. What this means, in practical terms, is that the biology of the crew arriving at Proxima Centauri after 400 years would not be identical to the biology of the crew that launched. Not in their DNA sequence, that changes far too slowly for 4 centuries to make a significant difference, but in the expression of that DNA, in which genes are active, in how their immune systems are tuned, in how their stress responses work, in how their bodies regulate inflammation, circadian rhythm, metabolic rate, reproductive biology. They would be human, unambiguously, entirely human. But they would be a different kind of human than anyone alive on Earth today, shaped by an environment no previous human being had ever inhabited, carrying an epigenetic signature written by 400 years of interstellar crossing. The immunological implications of this deserve particular attention because they connect directly to one of the most dangerous potential moments of the entire mission: the first contact with the planetary environment of Proxima Centauri b, if the crew ever sets foot on its surface. Human immune systems are calibrated by exposure. The extraordinary complexity of our immune response, the ability to recognize and respond to thousands of different pathogens, to distinguish self from non-self, to mount targeted defenses against specific threats, is partly genetic but partly built through a lifetime of encounters with the microbial world. Children who grow up in diverse microbial environments tend to develop more robust, better calibrated immune systems than those raised in highly sterile conditions. This is one of the mechanisms behind what epidemiologists call the hygiene hypothesis. The observation that rising rates of allergies and autoimmune conditions in industrialized societies correlate with reduced early life exposure to diverse microorganisms. The ship is, by necessity, an extraordinarily controlled microbial environment, Every organism aboard, every bacterium, every fungus, every virus is there deliberately or accidentally, but in either case it is there within a closed system that has been sealed for centuries. The microbial diversity inside the ship would be a tiny, highly selected fraction of the diversity present in any natural terrestrial environment. The crew's immune systems, shaped across generations by this constrained microbial landscape, would be exquisitely tuned to the organisms present on the ship and potentially naive to everything else. If Proxima Centauri b has any biology, any microbial life, any biochemically active surface chemistry, any organic compounds that the immune system might interpret as foreign, the first crew members to descend to the surface would be stepping into an immunological unknown of the most profound kind. This is not a new concern. The Apollo astronauts were quarantined after returning from the moon precisely because no one was certain the lunar surface was biologically sterile, though it turned out to be. For a generation ship crew arriving at a potentially habitable exoplanet, the concern is orders of magnitude more serious, and the isolation works in both directions. Whatever biology the crew carries, the microbiome they have evolved with inside the ship across 4 centuries could itself represent a profound perturbation to any native biochemistry it encounters. The protocols for first surface contact would need to be extraordinarily careful, possibly the most carefully designed human activity ever undertaken. There is a subtler biological concern that sits alongside the immunological one, and it involves something called the gut microbiome, the community of roughly 38 trillion microorganisms living in the human digestive system, which we now understand to play roles far beyond simple digestion. The gut microbiome influences immune function, mental health, metabolic regulation, inflammatory response, and potentially aspects of cognition and behavior. It is, in a genuine sense, an organ, a distributed, living organ composed of organisms that are not genetically human, but are functionally essential to human health. That microbiome is shaped by diet, environment, social contact, and the microbial communities of the spaces we inhabit. On Earth, it is continuously refreshed and diversified by contact with soil, water, plants, animals, other people, and the vast microbial ecosystem of the natural world. On a generation ship, that continuous refreshment stops. The microbiome becomes a closed system, just like everything else aboard. It evolves within the constraints of the ship's environment, shaped by whatever microbial diversity was present at launch and whatever has happened to that diversity across generations. Research on isolated human populations, Antarctic winter-over crews, long-duration submarine crews shows that gut microbiome diversity decreases measurably during extended isolation. The community simplifies. Certain species that depend on dietary inputs or environmental exposures not present in isolation gradually disappear. Others that thrive in the available conditions may become dominant in ways that would not occur in a more diverse, open environment. Over 400 years, those shifts could be significant. The arriving crew's gut microbiome might be substantially different from that of any Earth-based human population, potentially lacking species that play important roles in health outcomes, potentially harboring species in proportions that would be considered dysbiotic by contemporary medical standards. The medical implications of this are genuinely unclear because we simply do not have data on multi-generational microbiome evolution in isolation. This is precisely the kind of question that cannot be answered from Earth with current technology within any reasonable research timeframe. It is one of the deep biological unknowns of the generation ship concept. Now, let us talk about genetics more directly, because beyond epigenetics, beyond the microbiome, there are concerns about the genetic composition of the founding population that become increasingly important the longer the voyage lasts. Earlier, we discussed the population genetics research, suggesting a minimum founding population in the range of 14,000 to 40,000 individuals for genetic viability across a multi-century voyage. Let us dig into why those numbers matter, because the reasoning reveals something genuinely fascinating about how genetic diversity works in isolated populations. When a small group of individuals is separated from a larger population and reproduces in isolation, the genetic diversity of that founding group sets a hard ceiling on the diversity available to all subsequent generations. This is the founder effect. Over time, random chance determines which genetic variants get passed on and which do not, a process called genetic drift. And in a small population, drift is powerful enough to cause variants to be lost or fixed entirely regardless of whether they are beneficial, neutral, or harmful. In a large interconnected population like the current global human population, this random drift is counteracted by the enormous number of individuals carrying each variant, by migration and interbreeding between groups, and by natural selection weeding out harmful variants before they can accumulate. In an isolated population of even a few thousand individuals, those counteracting forces are dramatically weaker. Harmful recessive variants, genes that cause problems only when inherited from both parents, can increase in frequency simply through random drift, eventually reaching a prevalence where a significant proportion of the population carries two copies. This is called inbreeding depression, and its effects on health and vitality are well documented in isolated animal populations and historically in isolated human communities. The solution most seriously proposed is a combination of careful genetic banking, preserving the genetic diversity of the founding population in stored biological samples, and active genomic medicine. If the ship carries a comprehensive genetic library and the medical technology to use it, genetic diversity can be artificially maintained by introducing stored genetic material into the population at intervals. In effect, the genetic ghosts of ancestors who died generations ago continue contributing to the biological diversity of the living population, preventing the narrowing that isolation would otherwise cause. This is not science fiction. The underlying technology, sequencing, storage, and utilization of genetic material exists today in preliminary form, scaling it to the requirements of a century-spanning mission and maintaining it reliably across 400 years without degradation or institutional failure is the engineering challenge. But the biological rationale is straightforwardly sound. Here is where the biology intersects with something that feels more philosophical, and I want to sit with it for a moment because I think it is important. Across 400 years of epigenetic drift, microbiome evolution, and the selective pressures of a completely novel environment, the people who arrive at Proxima Centauri will be biologically distinct from the people who left Earth. Not in any dramatic, visible way, not a different species, not even necessarily a different subspecies in any formal taxonomic sense, but measurably, meaningfully different at the molecular level, shaped by an environment no previous human had ever inhabited, carrying biological signatures written by 4 centuries of the void. And here is the question that I find genuinely hard to shake. When those people land on Proxima Centauri b, if they land, if it is habitable, if the surface permits it, and when the first generation is born there, under that dim red star, in whatever atmosphere exists, shaped by that planet's gravity and radiation and microbial environment, what are they? They are human. Of course they are human. There is no biological threshold being crossed, no magic moment of speciation. But they are also something that has never existed before. People shaped, at the most fundamental biological level, by a world that is not Earth, carrying the epigenetic memory of a 400-year crossing in their cellular machinery, with immune systems tuned to the ship, and now being recalibrated to a planet, with gut microbiomes encountering an entirely alien biochemical environment for the first time. The first children born on Proxima Centauri b, if children are born there, will be the first human beings in history who are native to another star system, not travelers, not colonists in the historical sense of people who came from somewhere else. Natives, people for whom that world, that star, that sky is simply home, who have never known any other. The distance between them and us, culturally, experientially, biologically, will be as vast as the distance the ship crossed to get there. In a very real sense, they will be the first of something new, not post-human in any dramatic science fiction sense, just genuinely, irreversibly, beautifully other. There is a concept in evolutionary biology called phenotypic plasticity, the ability of an organism with a given genetic sequence to express different physical and physiological characteristics depending on the environment it develops in. Human beings have extraordinary phenotypic plasticity compared to most species. We are built to adapt. Our bodies, our brains, our immune systems, our hormonal profiles, all of them respond to environmental conditions in ways that allow individuals to function across an enormous range of circumstances. This plasticity is, in a very real sense, what makes the generation ship biologically plausible at all. We are not a species optimized for a single environment. We are a species optimized for adaptation. The same biological flexibility that allowed our ancestors to spread from equatorial Africa to Arctic tundra, to high-altitude plateaus, to tropical rainforests, to deserts, all while remaining recognizably and functionally the same species, is the flexibility that might allow our descendants to survive and eventually thrive in the novel environment of a generation ship and, perhaps, the surface of a world around another star. The cosmos shaped the atoms that became us. The stars that exploded before our sun existed seeded the molecular cloud that eventually condensed into our solar system and our planet and our biology. Every atom of calcium in your bones, every atom of iron in your blood was forged in the nuclear heart of a star that lived and died before Earth existed. We are, in the most literal and non-metaphorical sense possible, made of stardust. A generation ship returning some of that stardust to the stars, carrying biology built from stellar material back out into the galaxy from which it came, is not a violation of some natural order. It is a continuation of one. The universe made us curious. It made us restless. It made us look at points of light in the dark and want to know what they are. And now, 4 billion years into the experiment of life on this pale blue rock, we are beginning to seriously ask whether we can carry that experiment to other rocks, around other fires, in other corners of this extraordinary cosmos. The generation ship is the most audacious answer anyone has ever proposed to that question. And the biology, the messy, uncertain, genuinely unresolved biology of what happens to human bodies and human genomes across centuries of interstellar crossing, is not an argument against it. It is an argument for taking it seriously, for investing in the research, for building the knowledge base that could, someday, make the biological risks of such a voyage manageable rather than simply terrifying, because the alternative is staying. And staying, for a species as curious and as restless as ours, is its own kind of slow extinction, not of the body, but of the spirit that looks at the stars and refuses to accept that they are simply decoration. The generation ship is hard, brutally, almost incomprehensibly hard. The physics is hard, the engineering is hard, the social dynamics are hard, the genetics and the biology are hard. The psychology, stretched across 4 centuries, is perhaps the hardest of all, but hard is not the same as impossible. And impossible is a word that has a poor historical track record when applied to human ambition pointed at the sky. There is a clock on the ship, and there is a clock on Earth, and they are not ticking at the same rate. This is not a metaphor, it is not poetic license, it is one of the most rigorously tested, experimentally verified, mathematically precise predictions in the history of physics. And it emerges from a theory that Albert Einstein published in 1905, special relativity, which fundamentally rewrote our understanding of what time actually is at the deepest level we have yet managed to reach. Here is the core of it, stated as simply as the idea allows. Time is not a universal constant. It does not flow at the same rate for all observers in all situations. The rate at which time passes for any given object depends on how fast that object is moving relative to other objects, and on the strength of the gravitational field it inhabits. The faster you move, the slower your clock ticks relative to a stationary observer. The stronger the gravitational field you sit in, the slower your clock ticks relative to someone in a weaker field. These effects are real. They have been measured. GPS satellites orbiting Earth at high velocity and in a weaker gravitational field than the surface experience time at a different rate than clocks on the ground, and the GPS system must actively correct for this difference to maintain positional accuracy. Without those relativistic corrections, GPS would drift by roughly 11 kilometers per day. The fact that your navigation app works is, in a small but genuine sense, experimental confirmation of Einstein's theory running in the background of everyday life. Now apply that to a generation ship moving at a significant fraction of the speed of light. The relevant equation here is the Lorentz factor, named after the Dutch physicist Hendrik Lorentz, who derived it before Einstein, but without the theoretical framework to fully understand its meaning. The Lorentz factor describes how much time dilation occurs at a given velocity. At low speeds, anything humans have ever traveled at before the space age, the factor is so close to 1 that it is completely undetectable. Even at the orbital velocity of the International Space Station, roughly 28,000 kilometers per hour, the time dilation experienced by astronauts over a 6-month mission amounts to a few milliseconds, real, measurable, but not existentially significant. At 1% of the speed of light, roughly 3,000 kilometers per second, the Lorentz factor is approximately 1.0005. For every year that passes on Earth, the crew of the generation ship experiences approximately 1 year minus about 4.5 hours. Over the entire 400-year voyage, that accumulates to a discrepancy of roughly 75 days. The crew arrives at Proxima Centauri about 75 days younger than they would have been if they had somehow remained stationary relative to Earth, 75 days across 400 years. Meaningful, measurable, but not dramatic. The generation ship at 1% of the speed of light is not a vessel that exploits time dilation in any practically significant way, but push the velocity to 5% of the speed of light and the arithmetic changes. The Lorentz factor at 5% is approximately 1.600125. Over the 85-year voyage at that speed, the crew experiences roughly 38 days less than Earth clocks measure. Still modest, still not the dramatic asymmetry that science fiction tends to dramatize. To get truly significant time dilation, the kind where crew members age meaningfully less than people on Earth, you need velocities above roughly 10 or 20% of the speed of light. At 50%, a year on the ship corresponds to about 1.15 years on Earth. At 90%, the ratio is more than 2 to 1. At 99%, time on the ship runs at roughly 1/7 the rate of time on Earth. A generation ship is not going to reach those velocities with any propulsion technology currently conceived as feasible. The energy requirements scale with the Lorentz factor in ways that become almost incomprehensibly demanding at relativistic speeds. For the realistic velocity range of a generation ship, 1 to 5% of the speed of light, time dilation is a real effect, carefully measurable with precise instruments, but not a dominant feature of the human experience aboard. And yet, even at these modest relativistic velocities, something genuinely strange happens to the relationship between the ship and the universe it moves through. Something beyond simple time dilation, something that touches on the nature of simultaneity itself. One of the most disorienting implications of special relativity is that two observers moving at different velocities relative to each other do not agree on which events are simultaneous. Events that appear to happen at the same moment to one observer appear to happen at different moments to another, depending on their relative motion. This is not an illusion or a measurement error. It is a fundamental feature of the geometry of spacetime. For the generation ship crew, this means that the concept of what is happening on Earth right now is not as straightforward as it seems. When a crew member thinks about their great-grandchildren's great-grandchildren living on Earth, however many generations removed the arrival crew is from the launch, they cannot define a precise moment on Earth that corresponds to their own present moment without specifying a reference frame. The question, what time is it on Earth right now, has a different answer depending on how you are moving at the velocities we are discussing. This effect is subtle. The disagreement about simultaneity between a crew member on the ship and an observer on Earth amounts to a difference of days or weeks over the entire voyage, not years or centuries. But the philosophical implication is profound regardless of magnitude. There is no single universal now. Time is not a river flowing at the same rate through all of space. It is a dimension, the fourth one, and like the three spatial dimensions, its experience depends on where you are and how you are moving through it. The generation ship crew in transit between stars inhabits a slightly different slice of space-time than anyone on Earth. Not dramatically different, but genuinely, physically, irrevocably different. This is the universe we actually live in, not the intuitive, Newtonian universe where time ticks uniformly forward for everyone everywhere, but a universe where time and space are interwoven into a single fabric, and motion through that fabric warps both in ways that are real, measured, and mathematically beautiful. Now let us consider what general relativity, Einstein's follow-on theory from 1915, which extended special relativity to include gravity and acceleration, adds to the picture. General relativity tells us that gravity is not a force in the traditional sense. It is the curvature of space-time caused by the presence of mass and energy. Massive objects, stars, planets, even the ship itself curve the space-time around them, and other objects move along the straightest possible paths through that curved geometry. What we experience as gravitational attraction is actually the result of following a curved path through curved space-time. For the generation ship, general relativity becomes particularly relevant during the acceleration and deceleration phases of the voyage. When the ship's engines fire, pushing the vessel to cruise velocity at the beginning and slowing it down at the end, the crew experiences a force indistinguishable from gravity. This is the equivalence principle, one of the foundational insights of general relativity. The experience of acceleration and the experience of gravitational force are physically identical. You cannot tell, from inside an accelerating compartment with no windows, whether you are sitting on the surface of a planet or accelerating through space. This equivalence is what makes the rotating habitat concept work for simulating gravity during the cruise phase. It is also what tells us that any crew member who spends the acceleration phase in a part of the ship experiencing higher effective gravity, closer to the engine, perhaps in a more strongly accelerating region, will have their clock ticking at a slightly different rate than crew members in a weaker effective gravitational field elsewhere on the ship. The differences are minuscule, But the principle is real. The universe, it turns out, is stranger than our intuitions suggest at every level of examination. The deeper you look, the stranger it gets. And a generation ship, moving between stars at velocities that begin to bring relativistic effects into play, is a vessel navigating not just the physical distance between stars, but the curved, flexible, deeply counterintuitive geometry of space-time itself. Here is something that I find genuinely haunting about the relativistic aspect of this journey. Even at the modest time dilation the realistic velocities produce, imagine the ship launches today, or in 50 years. It does not matter exactly when. Pick a year. The crew is young, the engines are running, the solar system is receding behind them. Earth is sending messages, music, news, updates, transmissions from loved ones, scientific data, cultural output, the full stream of human civilization, compressed into electromagnetic signals and aimed at the departing vessel at the speed of light. In the first years, those signals arrive with only modest delay. The crew hears music recorded a few years ago, reads news that is a few years old. But the delay grows with distance. By the time the ship is 50 light-years out, the ship is heading to Proxima Centauri, only 4 light-years away. By the time the ship reaches the midpoint of the journey, messages from Earth are taking roughly 2 years to arrive. But here is the thing about those messages. They are not just carrying information, they are carrying time. Every transmission that arrives on the ship is a window into a moment that has already passed on Earth, irretrievably, permanently past. The crew is watching Earth's past arriving in real time, knowing that the present they are missing is inaccessible, not just distant, gone, existing only in whatever has already been transmitted and not yet received. If a child is born on Earth the day the ship launches, and the crew wants to watch that child grow up through transmitted video messages, they would see it happen in a strange, stretched, asynchronous way. The child's first steps arrive years late, their graduation, their adult life, their old age, all of it delayed, staggered, filtered through the growing distance between the ship and the world that sent it. By the time the ship arrives at Proxima Centauri, that child born on launch day would be a very old person on Earth, or dead, and the crew would still be receiving transmissions from their middle age, years behind the actual present. The ship is a time machine in the only real sense that phrase has ever meant anything. Not a device for moving through time, but a device for experiencing its passage at a distance, for watching history happen from outside it, for arriving at a destination in a future that everyone who said goodbye is no longer alive to share. The reverse is equally strange. Messages sent from the ship arrive on Earth years after they were recorded. A crew member who records a message at age 40 arrives, in that recording, as a 40-year-old to people who knew them as a 25-year-old. The aging happens, in the perception of Earth-based recipients, in discontinuous jumps, each new message a snapshot from a moment already receding into the past by the time it arrives. Relationships conducted across interstellar distances are relationships conducted across time as well as space. You are not talking to someone as they are now. You are talking to a version of them that existed years ago. Their response to your message when it arrives will be a response to a version of you that also existed years ago. The conversation is not between two present people. It is between two pasts, reaching toward each other across a gulf that neither can cross in real time. By the midpoint of the voyage, these correspondences would have taken on a quality more like historical correspondence than conversation. Reading a message from the ship would be like reading a letter from someone who, by the time you receive it, has lived an entire additional chapter of their life you know nothing about. The emotional texture of those exchanges, the intimacy and the distance, the warmth and the irreducible strangeness would be unlike any human communication that has ever existed. There is a mathematical object that physicists use to visualize these relationships, called a space-time diagram. On a space-time diagram, time runs vertically and space runs horizontally, and the paths of objects through space-time, called world lines, appear as lines traced across the diagram. Light travels at 45-degree angles in these diagrams because nothing moves faster. Everything slower than light traces a line at a steeper angle, closer to vertical, closer to the time axis. The world line of the generation ship, on a space-time diagram spanning 4 centuries and 4 light-years, would be a nearly vertical line with a slight lean toward the spatial axis, reflecting the ship's velocity, which is a small fraction of light speed. The world line of a light signal sent from Earth at launch would cut across the diagram at 45 degrees, catching up with the ship, because the ship is moving slower than light, but arriving later and later in the ship's time as the voyage progresses. Drawing that diagram, seeing the geometry of the journey laid out in space-time rather than just space, reveals something about the nature of this voyage that the conventional mental image of a ship moving through empty space does not capture. The ship is not just crossing distance, it is carving a path through the 4-dimensional fabric of reality. It is writing its history into the structure of space-time itself as permanently and as physically as any world line ever traced by any object in the universe. That path will have happened. Whatever the outcome, whether the mission succeeds or fails, whether the crew arrives or does not, whether Proxima Centauri b is a world worth reaching, the journey will have been real. The space-time interval will have been crossed. The universe will be permanently, if invisibly, different for having contained it. There is something about that permanence. The way physics insists that the past is real, that events that have occurred cannot be made not to have occurred, that every moment leaves an indelible mark on the structure of space-time, that I find genuinely comforting when I think about the difficulty and uncertainty of a mission like this. Whatever happens, it happened. It was real. Now let us bring this back to the ship and the people inside it, because there is one more relativistic effect worth discussing, and it is the one that connects most directly to the everyday experience of the crew. As the ship accelerates to cruise velocity, everything aboard it, every atom of hull, every liter of water, every living cell, gains kinetic energy in the reference frame of the external universe. This energy manifests as the time dilation and length contraction described by special relativity. From the crew's perspective, none of this is directly perceptible. The ship feels the same. Their clocks tick normally. Their heartbeats are regular. Nothing inside the vessel signals that they are moving at thousands of kilometers per second relative to the stars outside. But the universe they observe through their instruments changes. The stars ahead blue shift, the stars behind red shift, the cosmic microwave background radiation, the faint afterglow of the Big Bang, pervading all of space at an average temperature of 2.7 Kelvin, shifts in the forward direction toward higher frequencies and higher effective temperature. The radiation environment in the forward hemisphere of the ship becomes more energetic, not just because of particle impacts from the interstellar medium, but because the ship's own velocity is blue shifting the photons arriving from ahead at 5% of the speed of light. These effects are small but detectable with instruments. At higher velocities, they become dominant features of the observable universe from inside the ship. The cosmos does not look the same from a moving frame. The universe that the generation ship crew inhabits, the one they see through their telescopes, measure with their instruments, navigate by, is a velocity-shifted, aberration-distorted, relativistically transformed version of the universe we observe from our stationary vantage point on Earth. They are looking at the same universe, but they are seeing it differently, as they always will from wherever they end up, under whatever star they eventually call their own. Here is the deepest thing I want to leave you with from this part of the journey. Special relativity tells us that there is no privileged reference frame in the universe, no position that is truly stationary, no clock that is objectively correct while all others are wrong. Every observer, moving at every velocity in every gravitational environment, experiences a valid and physically consistent version of reality. The universe does not have a center. It does not have a preferred direction. It does not have a master clock against which all others are measured. The generation ship crew, moving at 1% of the speed of light through the interstellar void, inhabits a reference frame as physically legitimate as ours. Their time is as real as our time. Their universe is as real as our universe. The slight differences in clock rate, in stellar positions, in the color of the light reaching them, these are not distortions of some true reality. They are the reality. Different slices of the same four-dimensional space-time, each equally valid, each equally real. We tend to think of the cosmos as something out there, something we observe from a fixed point, as though we are standing still, and the universe is the thing that moves. But we are not standing still. We never have been. The Earth orbits the Sun at roughly 30 kilometers per second. The Sun orbits the galactic center at roughly 220 kilometers per second. The Milky Way moves through the local group of galaxies. The local group moves through the local supercluster. Everything is moving. Everything has always been moving. The generation ship crew, adding their own velocity vector to this already extraordinary cosmic dance, are not doing something alien to the nature of things. They are doing what everything in the universe does. Moving through space-time, tracing a world line, experiencing the universe from exactly where they are. The difference is that they chose their trajectory and they aimed it at a star. If you are still watching, then this channel was made for you. Don't forget to give this video a like and subscribe. Every video we take a real question about the cosmos and follow it all the way down. The signal arrives at the speed of light 4 years and 3 months after it was sent. 4 years and 3 months of crossing the same void the ship spent centuries crossing, compressed now into the travel time of a photon. It reaches the first antenna array pointed in the right direction. Someone, somewhere on Earth or in orbit around it, receives a transmission from the Proxima Centauri system. From human beings living around another star, think about what that moment means. Not for the crew, we will get to them, but for the people on Earth receiving that signal. For whatever civilization exists 400 years from now, going about whatever version of daily life 4 centuries of technological and social evolution has produced, somewhere in the middle of that ordinary day, a message arrives from the dark, from people who are the descendants of people who left, who crossed the void, who made it every previous moment in the history of human exploration, every coastline rounded, every continent reached, every ocean crossed, every summit climbed, was known about within days or weeks or months. The news traveled at the speed of ships, of horses, of telegraph lines, of radio waves bouncing through an atmosphere. But this signal, this confirmation that humanity has become an interstellar species, travels at the speed of light from a distance that makes even light take years to cross. The celebration, when it comes, will be for something that happened 4 years ago. The crew being celebrated will have moved on, will have done 4 more years of work, will have aged 4 more years, will have had questions and crises and discoveries and births and deaths in the intervening time that Earth knows nothing about yet. The moment of arrival, by the time it is known on Earth, is already history. That is interstellar communication. That is the texture of what it means to be a multistellar civilization. Not real-time connection, not shared experience, but a kind of deep, slow, asynchronous intimacy across the dark. Messages like letters from a very distant friend, arriving years late, carrying the weight of everything that happened in between, let us stand at the moment of arrival itself, inside the ship. From the crew's perspective, the deceleration phase has been underway for years, perhaps a decade or more, depending on the propulsion architecture and the initial cruise velocity. The engines have been firing in reverse, pushing against the direction of motion, gradually bleeding off the velocity accumulated during the acceleration phase a generation or more ago. The magnetic sail, if that is the chosen deceleration method, has been deployed, a vast invisible structure extending far ahead of the ship, catching the stellar wind of Proxima Centauri, translating it into drag, into slowing, into the long controlled fall toward a new star, and that star has been growing, slowly at first, barely distinguishable from its appearance a year ago, a decade ago, then faster, resolving from a point into a disk, dim and reddish, casting a light that is warmer in color than sunlight but cooler in intensity. The first star, other than our sun, that any human eye has ever seen as something other than a point. The crew, the generation alive at arrival who have no more personal memory of the launch than we have personal memory of events 5 centuries before our birth, would have grown up with this moment as mythology. The arrival, the thing the ship was built for, the reason every sacrifice their ancestors made was worth making. They have heard about it their entire lives. They have rehearsed the protocols. They have trained for the survey operations, the orbital insertion procedures, the instrument calibrations required to begin the systematic study of the system they are entering. And now it is happening, not in a recording, not in a mission document, not in the testimony of a great-great-grandparent preserved in the ship's archive, actually happening. Outside the viewports, growing brighter every day, the star that is now their star, the first instruments to return meaningful data would be those sensitive to the broad-spectrum electromagnetic output of the system: radio, infrared visible light, ultraviolet, X-ray. A picture of the system would begin assembling itself in the crew's computers from these data streams, building up resolution and detail as the ship approaches. Planets would resolve from points into disks. Surface features, if any exist beneath any clouds or atmosphere, might begin to emerge in the highest resolution imaging systems, and then the atmospheric spectroscopy data would come in. This is the measurement that every exoplanet astronomer on Earth has been working toward for decades with increasingly powerful space telescopes. The chemical fingerprint of a planetary atmosphere, revealed by the way it absorbs specific wavelengths of light passing through it: oxygen, carbon dioxide, water vapor, methane, ozone. The specific mix of molecules present in a planetary atmosphere tells you an enormous amount about the processes generating them, whether geological, chemical, or potentially biological, from Earth. Getting this data for Proxima Centauri b is extraordinarily difficult because the planet does not transit its star from our viewing angle, meaning we cannot use the standard technique of watching starlight filter through the atmosphere during a planetary transit. Future space telescopes might achieve direct imaging sensitive enough to collect the planet's own light and analyze its spectrum. But from Earth, with our current or near-future instruments, we are working at the absolute edge of what is technically possible. From orbit around Proxima Centauri, the measurement is straightforward. You are there. The planet is in front of you. You point your spectrometer at it and read what comes back. The data that Earth-based astronomers might spend decades trying to tease out of indirect measurements arrives in hours. Clear, unambiguous, real. Whatever that data says, whatever the atmosphere of Proxima Centauri b turns out to contain, the crew will know it with a certainty that no Earth-based observation can match. And they will be the ones who have to decide what to do with the answer. Let us consider, carefully, the different scenarios the atmospheric data might reveal. Because this is not a situation with one obvious outcome, the range of possibilities is genuinely wide, and each one leads to a different version of what comes next. Scenario 1. The atmosphere is thick and reasonably Earth-like in composition. Significant nitrogen, detectable oxygen, water vapor, manageable carbon dioxide levels. Surface pressure in a range compatible with unprotected human physiology, or close enough that modest pressure suits would suffice. This is the best-case scenario, and in honest scientific terms, it is probably not the most likely one given what we know about flare activity and atmospheric erosion, but it is not impossible. If the planet formed with a substantial volatile inventory, if it has ongoing geological activity replenishing its atmosphere, if its magnetic field proved stronger than our current models predict, a genuinely habitable surface is not ruled out. In this scenario, the crew faces a decision of almost incomprehensible weight. Do they descend? The protocols presumably say yes. This is what the mission was built for. But the immunological concerns we discussed earlier are fully in play. The crew's immune systems, tuned to the ship's microbial environment across 4 centuries, would be encountering a completely alien biochemical landscape. The first people to set foot on the surface would be doing something with no precedent in human history, not just geographic exploration. Biological first contact with an entirely separate biochemical world. Scenario 2. The atmosphere exists, but is not directly breathable. Too thin, wrong composition, too much carbon dioxide, too little oxygen, or otherwise requiring life support for human surface activity, but not entirely absent. This is perhaps the most scientifically interesting scenario, because a non-breathable but present atmosphere implies ongoing processes generating and replenishing it. Volcanic outgassing, photochemical reactions, possibly even biological metabolism. An atmosphere that exists but does not yet support human life unaided might, with enough time and the right interventions, be modified. The concept of terraforming, the deliberate modification of a planetary atmosphere and surface to make it more hospitable to Earth life, is speculative technology, but it has a serious scientific literature behind it. The timescales involved are typically thousands to millions of years, but a civilization already committed to a 400-year crossing might find that perspective manageable. Scenario 3. The atmosphere has been substantially stripped away. The surface is directly exposed to stellar wind and flare radiation. Whatever volatile inventory the planet once had has been eroded over billions of years of proximity to an active flare star. The surface is bare rock under a dim reddish sky, not quite a sky, more an extremely thin wisp of residual gas, with radiation levels that would kill an unprotected human in hours. This is the scenario that current models, honestly assessed, consider reasonably probable. It does not mean the mission has failed. It means the mission has discovered the truth about a world that humanity had been speculating about for centuries. That truth has scientific value beyond calculation, and the system still contains resources, asteroid belts, cometary bodies, the gravitational relationship with the Alpha Centauri binary that a technologically capable civilization could exploit. Regardless of which scenario unfolds, there is something the crew would do that I think is often overlooked in the engineering-focused discussions of arrival. They would grieve, not necessarily loudly, not necessarily in a way that is articulated or even consciously recognized, but the arrival at Proxima Centauri, after 400 years of sacrifice, after everything that was given to reach this point, would carry an enormous emotional weight that no technical briefing could prepare them for. The moment when the data comes back and tells them, in precise spectroscopic language, what they actually have is a moment of confrontation with reality, not with the imagined destination that has been carried through generations of stories and mission documents and cultural mythology, with the actual planet, the real thing, whatever it turns out to be. If it is less than hoped, if the surface is hostile, if the atmosphere is thin, if the prospect of a human settlement on the surface seems distant or impossible, the crew does not have the option of being disappointed and going home. They are home. This is what they crossed 40 trillion kilometers to find, and they have to live with it, have to build something from it, have to make it mean something, even if it is not what anyone imagined. That is a human experience of remarkable depth. The confrontation between expectation and reality played out against the backdrop of everything a civilization sacrificed to reach this moment. There is grief in that. There is also, if the crew is made of the right stuff, and presumably they would be, shaped by 4 centuries of selection for resilience and adaptability, something else. A recognition that this is not the end of the story, it is the beginning of a new chapter, written in a place no human hand has ever touched. What would they build first? Assuming the surface is not immediately accessible, either because it is hostile or because proper survey and safety protocols require time before any descent, the first permanent human structure in another star system would almost certainly be orbital, a habitat, an expansion of the ship itself, or a station assembled from materials extracted from local asteroids or the outer reaches of the system, something that says, in the most physical and concrete way possible, we are staying. This is not a visit, this is a settlement. The psychological importance of that first permanent structure, of driving the first anchor into the new system, of constructing something that is not designed to move, that is built for a future rather than a journey, would be profound. The ship has been home for 400 years, but it was always a vehicle, a means to an end, a world in motion. The first fixed habitat around Proxima Centauri would be something different, a place. The first human place in another star system, whatever it looks like, whatever materials it is built from, whatever architectural choices the crew makes, whatever name they give it, it would represent a threshold as significant as any in human history. The moment we stopped being a single-star civilization, the moment the solar system stopped being the boundary of human habitation and became, instead, our place of origin, there is a word for the star system you come from when you have left it, when it is not where you live anymore, but where your ancestors came from, when it is history rather than home. We do not have that word yet. The crew would need to invent it. Let us think about what the crew sends back. Not just the confirmation signal, not just the scientific data, but the human content of their first transmissions. What do you say? When you have arrived somewhere no one has ever been, and you want to tell the people who sent you what it is like, you cannot describe it in terms they already understand. There is no reference point, no comparable experience to anchor the description. You are trying to communicate the texture of an alien star system, the specific quality of its light, the shape of its planetary bodies hanging in an unfamiliar sky, the readings of instruments that have never pointed at this particular corner of the universe before. To people who have never left their own solar system and never will, the crew would find new language. They would have to. 400 years of cultural and linguistic evolution inside the ship would already have produced a version of whatever language they started with that is noticeably different from what Earth speaks. Their idioms, their metaphors, their ways of describing experience would have been shaped by an environment utterly unlike anything on Earth. And now they have arrived somewhere that pushes even that evolved language to its limits. The transmissions that eventually reach Earth would be among the most extraordinary documents in human history. Whatever they contain, technical data, personal testimony, attempts at poetry, recordings of the crew gathered around a viewport staring at a planet no human eye has ever seen up close. They would be read and reread, studied and debated, treasured and argued over, for as long as human civilization exists to care about them, and they would arrive 4 years and 3 months after they were sent. After the moment they describe is already past. After the crew has moved on to the next thing, the next challenge, the next question, the transmissions would be dispatches from a past that only the crew has lived, arriving into a future the crew cannot see. That is the nature of interstellar civilization, not a unified, connected community, a constellation of separate points of light, each shining with its own history, communicating across the dark in slow, asynchronous, deeply precious exchanges, each message carrying not just information but time, not just data but the irreducible weight of human experience, compressed into electromagnetic pulses and sent across the void at the only speed the universe allows. There is one more thing I want to sit with before we reach the final part of this journey, something that the generation ship, more than any other concept in the human relationship with space, forces us to confront directly. What is humanity? Not in the biological sense, we have covered that. Not in the genetic or epigenetic or microbiological sense, but in the deeper sense. The sense that asks what it means to be one thing when that thing has been separated across stellar distances, has evolved in different environments, has developed different languages and cultures and values and ways of understanding the universe 400 years after the ship launches. The people on Earth and the people around Proxima Centauri will be so different, culturally, experientially, linguistically, biologically in the epigenetic sense, that they may barely recognize each other as the same thing. Communication will be possible technically, but the gap in shared experience will be vast. The references that feel obvious to an Earth dweller will be obscure to someone who has never seen a natural sky. The references that feel obvious to someone born in a generation ship will be incomprehensible to someone who has never spent a day in an enclosed, recycled air, artificial light environment. And yet, they will both be human. They will both look at the stars and feel something. They will both love and grieve and wonder and create. They will both ask questions about the universe that they cannot yet answer. They will both, somewhere in the middle of an ordinary day, stop and look out at the sky, whatever sky is available to them, and feel the pull of the unknown. That pull is perhaps the most persistent and most distinctively human thing about us. Not our technology, not our social structures, not our language or our art or our science, extraordinary as all of those are. The pull, the reaching, the refusal to accept that the edge of the known is the edge of what matters. The generation ship is the most extreme expression of that refusal in the entire history of our species. And the people who eventually build it, board it, ride it across the void, raise children in it, grow old in it, die in it, and ultimately arrive in a new star system, those people will not be doing something alien to human nature. They will be doing the most human thing imaginable. Every civilization that has ever existed on this planet has looked up, not metaphorically, literally, physically tilted their heads toward the sky and looked at what was there. The Babylonians mapped the wandering points of light and built mathematics to predict their movements. The Polynesian navigators read the stars like a language, crossing the largest ocean on Earth with no instruments beyond their own knowledge of the sky. The ancient Egyptians aligned their most sacred structures to stellar risings with a precision that still impresses modern astronomers. The Maya built observatories. The Chinese kept astronomical records stretching back millennia. Every culture on every continent across every era of human history looked up and felt that the sky was not just backdrop, that it meant something, that it was connected in some deep and not entirely articulable way to who they were and what they were doing here. We have never stopped looking. We just keep building better eyes. And now, for the first time in the history of our species, the looking has become specific enough, technical enough, scientifically grounded enough that we can actually see individual planets around other stars. We can measure the chemistry of their atmospheres. We can calculate whether liquid water might exist on their surfaces. We can identify candidates, actual, named, specific worlds where the conditions for life as we understand it might be present, not vague regions of sky. Worlds, real ones. Proxima Centauri b is one of them, the closest one, the one that is, by the brutal arithmetic of interstellar distances, the most reachable thing beyond our own solar system. A world that might be habitable, orbiting a star that is close enough that human beings have, in all seriousness, begun drawing up engineering concepts for how to reach it. That is an extraordinary moment in history, and I am not sure we are treating it with the seriousness it deserves. Let us talk about the Fermi paradox one final time, because the generation ship leads directly to its most unsettling implication. The Fermi paradox, the collision between the apparent likelihood of extraterrestrial civilizations and our complete failure to detect any evidence of them, has many proposed resolutions. The Great Filter hypothesis is perhaps the most discussed. The idea that somewhere between the origin of life and the development of spacefaring civilization, there is a filter, a barrier, something that almost no species survives. And that filter is either behind us, somewhere in the transition from chemistry to biology, from single cells to complex organisms, from organisms to intelligence, or it is ahead of us, still waiting. If the filter is behind us, the silence of the cosmos is explained by how extraordinarily rare it is to get this far. We got lucky. Life is rare. Intelligence is rarer. We are possibly alone or nearly alone in a galaxy of 400 billion stars, and the vast quiet of the sky reflects not the absence of possibility, but the savage difficulty of the path. The silence means we are a miracle. If the filter is ahead of us, the implications are darker. The silence means that civilizations like ours, civilizations that develop technology, that figure out physics, that look up and begin to understand what they are looking at, regularly fail to survive long enough or become spacefaring enough to leave a detectable mark on the galaxy. The silence means the universe is littered with the ruins of civilizations that almost made it, and we are the next candidate. The generation ship in this context is not just an engineering project. It is a response to the Fermi paradox, a physical, practical, deeply serious attempt to ensure that whatever happens to Earth, whatever catastrophe or conflict or slow decline or sudden ending befalls the civilization that built the ship, something survives, something crosses the gap, something plants a flag in another star system and says, in the most permanent way available, we were here, and we are still here, and we are not done yet. The generation ship is the answer to the great filter, or rather, it is the attempt to be the answer, to be the civilization that makes it through. That does not get filtered, that continues. There is a version of this argument that makes the generation ship not just desirable, but morally urgent. If we take seriously the possibility that intelligent life is rare, that we might be among the only minds in the galaxy complex enough to understand the universe and ask questions about it, then the preservation of that mind across as many locations as possible becomes something close to an ethical imperative, not for our own sake alone, but for the universe's sake. The universe is approximately 13.8 billion years old. For most of that time, as far as we can tell, there was no one in it to notice, no mind to observe the beauty of a supernova, to feel the vertigo of a deep field image showing 10,000 galaxies, to work out the mathematics that describes how gravity curves space-time. The cosmos existed, magnificently, terrifyingly, at incomprehensible scale, and there was no one to appreciate it, no one to be moved by it, no one to ask why. We are, as far as we know, among the first minds the universe has produced that are capable of understanding their own situation, of knowing that we exist on a small planet around an ordinary star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies, and feeling the full weight of that knowledge, of looking up and not just seeing light but understanding what it means, how far it has traveled, what is producing it, what it tells us about the physics that governs everything. That is extraordinary. That might be rare beyond our ability to calculate, and if it is rare, then the loss of it, the extinction of minds capable of understanding and appreciating the cosmos, would be a loss not just for us, but for the universe that produced us. The generation ship in this framing is an act of cosmic responsibility. The decision to spread, to reach, to ensure that the experiment of mind does not end with a single planet. Not because we are the most important thing in the universe, but because we might be the only thing in this corner of it that is paying attention. Now I want to be honest about something, because this video has been, throughout, committed to honesty, to the real physics, the real biology, the real engineering challenges, the real human difficulties. And honest engagement with the generation ship concept requires acknowledging that it is also, in very important ways, terrifying. The people who launch it will never arrive. The people who arrive will never have launched. Every generation in between will live and die inside a vessel they did not choose to board, committed to a destination they will never see, for a mission whose success they will never know. The ethical questions embedded in that, the right of the founding generation to conscript all subsequent generations into a mission without their consent, the psychological implications of a life bounded by metal walls and recycled air, and the knowledge that the stars outside are not destinations but background. Those questions do not have clean answers. We have spent time in this video on the engineering of the ship, the physics of the journey, the biology of the crew, the psychology of the long crossing. But underlying all of it is a more fundamental question that engineering cannot answer and physics cannot resolve. What do we owe to the people who will be born on that ship? What responsibilities does the civilization that launches it have to the generations it creates in transit who had no voice in the decision and no way to opt out? Different ethical frameworks give different answers. A utilitarian calculus might weigh the potential benefit to humanity's long-term survival against the cost to individual generations and conclude that the mission is justified. A rights-based framework might conclude that no generation can legitimately conscript an unborn one into any mission, regardless of the stakes. A virtue ethics approach might ask what kind of civilization we become by choosing to do this, and whether that civilization is one we want to be. These are not rhetorical questions. They are the actual ethical substance of the generation ship debate, and they deserve to be taken seriously rather than waved away by the grandeur of the ambition. What I believe, and this is belief, not physics, not biology, not engineering, but my own considered position, is that the generation ship is only ethical if it is also a good life, not just a sacrifice for future generations, not just a means to an end, but an existence that is genuinely worth having on its own terms, independent of the destination, a community that is meaningful, a society that is just and humane and curious and creative, a place where children born into the crossing have real lives, not just mission roles, where the journey itself is understood as something valuable, not merely instrumental. If the generation ship can be that, and I think it can, if we design it with that intention, if we take the social and psychological and cultural dimensions as seriously as the engineering ones, then the people born aboard it are not being wronged by their existence. They are being given a life that is, in many ways, richer in meaning and purpose and community than many lives lived on Earth, shaped by a unique and extraordinary context. part of something genuinely significant. That is not a small thing. That might, in fact, be the most important design requirement of all. Here is what I find most moving about the generation ship concept when I sit with it quietly and let it settle. It is an act of faith, not religious faith, though people of faith will certainly find their own meanings in it, but faith in the most fundamental sense. Confidence in something that cannot be directly verified, trust in a future that cannot be seen, the decision to commit enormous resources, enormous sacrifice, enormous human lives to an outcome that will not be known for centuries, by people who will not be there to see it. The civilization that builds and launches a generation ship is saying, in the most concrete and irreversible way possible, that it believes the future is worth investing in, that the human story is not finished, that the universe is worth exploring even when the exploration requires more than any single lifetime can contain, that some things matter enough to be worth dying for, or more precisely, worth living and dying for, without knowing whether they succeeded. That is an extraordinary statement, and it is also, in a quieter key, the statement that all meaningful human endeavor makes. Every cathedral ever built took longer than a single lifetime to complete. The people who laid the foundation stones did not see the finished spires. Every scientific research program that runs across generations, the mapping of the human genome, the long-term ecological studies that track ecosystems across decades and centuries, requires investment in a future that the investors will not fully inhabit. Every parent who raises a child is making a bet on a future they will only partially see, shaping a person who will go on to do things their parents cannot imagine. The generation ship is the grandest possible version of this, the most extreme expression of humanity's willingness to invest in what comes after, to care about the future more than our own survival within it. There is something about that, about the willingness to sacrifice for people not yet born, for outcomes not yet real, for a destination not yet reached, that feels like the best of what we are. Not the most powerful, not the most intelligent, but the most human, the most genuinely admirable, the capacity to love a future we will never inhabit. So where does that leave us? Here, now, on this planet, under this sky, the generation ship is not being built today. The propulsion technology required does not yet exist in practical form. The closed ecological systems that could sustain a multi-century voyage have not yet been demonstrated at anything approaching the necessary scale and reliability. The social and psychological science of multi-generational isolation is in its absolute infancy. The medicine, the genetics, the engineering, the governance frameworks, all of it needs centuries of development before the launch button can honestly be pressed. But the thinking is happening now. The physics has been known for decades. The population genetics research is current. The closed-loop life support science is advancing. The detection of exoplanets, including the specific detection of Proxima Centauri b and its siblings, is producing the destination intelligence that any real mission would require. We are not building the ship, but we are, in a very real sense, building the knowledge base from which the ship will eventually be built, and that matters, because the path from here to there is not a single leap. It is a series of steps, each one dependent on the ones before it. Longer and longer duration space habitation, more sophisticated closed ecological systems, a permanent lunar presence, a permanent Martian presence, decades of multi-generational station living, the gradual accumulation of experience with human life beyond Earth, each step building the knowledge and the capability for the next, across timescales that dwarf individual lives, but are entirely plausible for civilizations thinking in centuries rather than years. The generation ship is the horizon, the thing visible at the far edge of a trajectory that begins with choices we make today, about investment in science, about commitment to space exploration, about whether we believe the future is worth the cost of building it. The ship will not be built by any generation alive now, but it will be built or not built based on whether the generations alive now decided that it mattered. I want to close with something small, or rather something that seems small and is not tonight, or tomorrow night, or the next clear night you have. Go outside, away from the lights if you can manage it. Let your eyes adjust. It takes about 20 minutes for the eye to reach full dark adaptation, and most people never wait that long. Wait, let the sky come to you, and when it does, when the stars appear, not just the bright obvious ones but the fainter ones too, filling in the background with a depth that the light-polluted suburban sky never reveals, find the southern sky if you are in the right hemisphere, and look for a dim reddish point of light about 4 light-years away. You will not be able to pick Proxima Centauri out without a telescope. It is too faint, magnitude 11.1, far below the naked eye limit. But you can look in its direction. You can know it is there, 4 light-years. The distance that light, moving at the fastest speed the universe permits, covers in 4 years. The distance that sound, if it could travel through the vacuum, would take 4.5 million years to cross. The distance that any ship we could conceivably build in the next few centuries would need decades or centuries to traverse. The distance that, on a map of the galaxy, is essentially 0 neighboring stars in a galaxy 100,000 light-years wide, and around that star in a tight orbit, a world, perhaps dead, perhaps barely alive, perhaps breathing, in whatever alien way life manages to breathe when it arises in conditions we have never seen. We do not know. That is the honest answer. We do not know, but we are looking, and we are thinking, and some of us, the engineers and the physicists, and the population geneticists, and the closed-loop ecologists, and the social scientists, and the ethicists, some of us are beginning, seriously, carefully, with full awareness of how hard it is to plan. That is the most human thing I can imagine. Looking at a point of light that is too faint to see, knowing it is there, knowing what it represents, and beginning, slowly, carefully, across generations, to reach for it. We are made of stardust. Every atom in your body was forged in the nuclear furnace of a star that lived and died before our sun existed. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it scattered across space by a stellar explosion billions of years ago, gathered by gravity into this solar system, incorporated into this planet, organized by 4 billion years of biological evolution into the extraordinary complexity of a living, breathing, wondering mind. We are the universe becoming aware of itself, the cosmos folding back on its own history, asking where it came from and where it is going. We are how the universe looks at the stars, and someday, not soon, not easily, not without cost that we cannot yet fully imagine, we will not just look at them, we will go. But before you go, if this journey unsettled you even a little, you need to watch the video on screen next. We explore why interstellar travel would destroy us before we even arrived. And trust me, after everything we just covered, it hits differently.